So, good morning, everybody. I think we are about to start the workshop. But before we start, I'd like to actually... Hello? Yeah. I'd actually like to do some housekeeping first. Let me introduce myself. My name is Jochen Körner. I'm with the German Offshore Wind Energy Foundation, and I used to be the project manager for the foundation for the promotion project, and taking care of dissemination and communication measures. And it's definitely my pleasure to actually in 2021 see a promotion-related event like the WorkPackage 15 workshop on gas systems for Hvdc systems. Yeah, I'd like to welcome you and do some housekeeping first before I hand off to the former project coordinator, Cornelis Plate, and the organizer of this workshop, Uwe Richard. And yeah, before we do this, some housekeeping. So the workshop will be recorded, just to make everybody aware of that fact again. We will share the recording in an email with a link after the workshop has concluded, and reach out to you with the material we create during this workshop. All attendees right now, you may have noticed and realized, all attendees entering this stream are muted and the cameras are automatically turned off. This is to save bandwidth and make everything a little bit smoother. We will have parts in the program ready for interaction, namely discussions and your questions. So please, questions, if they come throughout the presentations, do phrase your questions in the chat and send them off to us. We will monitor the chat, we will collect the questions, and then we can address the questions in the fitting discussion and question periods later on. Everybody presenting today, just a note for you guys, we will hand over the steering wheel, so to say, to you when it's your time for presentation. So please prepare yourself to present from your machine. We did receive your copies of your presentations. So in case anything goes bing or you're having technical issues on your side, we can chip in and run the presentation from our side. But ideally, it would be good if you can do it on your side, on your machine, so you have full control about the presentation. I think I touched up upon the main things. Yes, so yeah, so much for the housekeeping. So right now I would like to hand over to Cornelis Plate, the former project coordinator of the promotion project, to give you a proper welcome into the workshop. Thank you for joining us again. Hope everybody had a nice transition into 2021, and I hope that you will enjoy the workshop. Thank you. Kees.
Great. Thank you, Jochen. Yeah, it's also my pleasure to still give an introduction to promotion already after the project is finished. You see here the title slide that we used for our final conference, the North Sea Grid for the European Green Deal. And that's really what promotion was about. How should we build a grid, an HVDC, preferably meshed HVDC grid in the North Sea to realize the objectives of the European Green Deal? I will tell you a little bit about the why we wanted to do this, then about what we've done, and then very briefly come to the main conclusions of the project. So let's first jump into the why. What you see here is a graph, which is basically an extract from a little bit of scenario work that we do in DNVGL every 2 years, called the Energy Transition Outlook. And this one of the outputs of this model is that it allows us to model the power line capacity needed in the world to realize the energy transition. And yeah, as we, I guess, in this virtual meeting are all HVDC engineers, you can interpret this as either good news or very bad news. There's a lot of work for us to come. You can see that the share of DC in the transmission line capacity increases significantly, and especially if you look at how it grows from where we are today. And this, of course, is driven by growth of renewables, and electrification of demand, and a different way of transmitting the energy from where it's generated to the consumers. Now, we see this happening in Europe as well, of course. Here you see a map that shows all the HVDC links that are currently either in operation or in planning in northwestern Europe, especially focusing around the North Sea. And if you look at this, you can see that we actually already have something like an HVDC grid in the North Sea, except that it isn't a grid. They're all separate, dedicated point-to-point links. You can see that each link here has a different color. So that means that it has a different voltage level. What you can also maybe see, or even though it may not be so clear from the image, is that each link here has a distinct purpose. So either it connects an offshore wind farm, or it is an interconnector, or it provides, for example, an oil and gas platform offshore with power from shore, or there are a few links that are providing basically reinforcements of the onshore AC grid through an offshore connection. And in none of these cases are these functions actually combined into the same infrastructure, which is what we see, of course, in the onshore grid. So one of the questions that we had in promotion is what do we need to do? What do we need to change from, for example, a regulatory perspective, a planning perspective, but also what technologies do we need in order to realize a grid where we connect all these different point-to-point links and realize a benefit of the combined use of the infrastructure and the most efficient application of these different technologies. So the first question is, of course, like, why do we need meshed HVDC grids offshore? To explain that, I have to go back to this point-to-point grid connection paradigm that I just showed you. This paradigm has worked very well for the early phases of offshore wind and interconnected development, but it suffers from a few drawbacks that make it less suitable for realizing the integration of large amounts of offshore wind power and interconnection capacity. Firstly, when you have these dedicated links, they can only be used for one purpose, such as the export of offshore wind power. And this means that in times of no wind, this actually quite costly infrastructure cannot be used or is not used. And that has a negative impact on the return on investment and therefore on the cost of energy and the socio-economic welfare such a link can realize. Secondly, if a failure occurs on this cable, the offshore wind farm or the country that it connects cannot receive or export power. And this has an immediate impact on the receiving country, which now has to source this power from elsewhere within milliseconds. In the long term, no wind energy can be exported or no interconnection trade can take place for the duration of the cable repair. And in the North Sea, where it can be quite stormy and pretty nasty weather, this can take months to do so. Now, both of these drawbacks can be mitigated by providing an additional link between the point-to-point connections, forming what we call a radial multi-terminal HVDC system. The extra link can act as a redundant path in case of an outage of one of the export links, and it can also combine the functions such as offshore wind export and interconnection of countries using the same infrastructure. And this forms what we call a hybrid asset. You may have heard this term before. Further functions can be added, such as serving offshore loads or realizing reinforcements of onshore AC grids. By combining these functions, the number of converters and the length of the cables that we need to realize this transmission need is minimized. And this, of course, leads to a reduction in the capital and the operating cost that is required for this offshore grid. It results in improved reliability, in reduced environmental impact, and in reduced impact on coastal communities. A further improvement can be made by realizing these nodes in the transmission grid on the DC side rather than on the AC side. And now we get what we call a meshed multi-terminal HVDC system. Meshed here means that there's always more than one path between any 2 points in a network. Of course, this is something that is already well known from the AC transmission grid. This reduces the number of converters that are required to build the system. Thus, in turn, further reduces the required capital cost. It reduces the required footprint, and it reduces maintenance requirements. And depending on what power flows are prevailing here, it also further reduces the losses, the annual losses that are incurred in this system. Moreover, it is now possible, in case of a fault on one of the HVDC cables, to immediately switch over to the redundant path formed by the meshed connection. By doing so, power can continue to be delivered to the onshore grid, thereby limiting the impact of the failure. And this becomes especially important when wind farms and the offshore transmission links become so large that the loss of one can jeopardize the stability of the onshore grid. So multi-terminal meshed HVDC grids hence improve the security of supply, they reduce the environmental impact and lower the cost of energy compared to the current point-to-point HVDC system building paradigm. So you may wonder, why have meshed HVDC systems not yet been built in Europe if they have so many potential benefits? The current point-to-point HVDC system building paradigm persists due to many technical, legal, regulatory, and system planning reasons. First of all, from a technical perspective, novel, previously unused technologies are necessary to build meshed HVDC networks. The converters and offshore wind farms need to be controlled to guarantee stable operation in both steady state and dynamic conditions. The power needs to be equally distributed among all the converters, also during changes in generated wind power or in case of faults in either the HVDC network or in one of the neighboring onshore AC networks. Moreover, the offshore wind farms are expected to take over some of the power system stabilizing roles that conventional power plants have today, which requires coordination of their control systems. In addition, to improve the security of supply, an HVDC network protection system must be installed, which continuously monitors the network to detect if and where faults occur. In case a fault is detected, the protection system decides on the best way to disconnect the smallest possible part of the HVDC network that contains the fault. And it has to do so quickly and selectively enough so that the operation in the healthy remainder of the network can be restored before the impact of the offshore DC fault on the onshore AC grids has become unacceptable. And to do so, HVDC circuit breakers and converters capable of interrupting DC fault currents are necessary to physically disconnect the faulty part of the network. And due to their high cost, this fault clearing equipment can only be placed at certain strategic locations in the network, balancing the protection selectivity with the impact of a DC fault on the onshore AC grid. To build the HVDC nodes offshore, gas-insulated substation equipment is necessary, which, by being 90% smaller than the air-insulated substation equipment, greatly reduces the cost of offshore platforms. Currently, the SF6 gas, which is used, has a strong greenhouse potential. So alternatives for this must be developed for use in future HVDC grids. And of course, we will hear more about this today. Now, these technologies to build multi-terminal HVDC networks were considered immature up to now, and due to a lack of testing procedures, standardization, and technical connection requirements, the equipment from different vendors was not interoperable with one another. Moreover, historically, different point-to-point HVDC projects were realized without future expansion into a multi-terminal HVDC grid in mind. They were physically located far apart and realized in different times, so their ratings and their layouts were optimized for their particular business case and not chosen to be compatible with any potential future neighboring links. And perhaps the biggest challenge is that there are borders of 6 different countries running through the North Sea. The national regulatory frameworks in the countries bordering the North Sea are adequate for the onshore AC grids, but have differences between them, which result in an unequal regulatory playing field offshore. Now, there has been some EU regulation that was designed to overcome this, but it did not foresee the need to combine the different purposes into the same infrastructure offshore. And that formed another hurdle in the uptake of the combined use of or the hybrid asset infrastructure, which we really see as the first building block of meshed offshore HVDC grids. The objective of promotion was to break through this status quo. So organized in 16 work packages, and over the course of the last 4.5 to 5 years, 34 partners have improved and matured the understanding of the required HVDC technology. So we researched, we analyzed, we modeled, we extensively simulated, and we compared the most promising network topologies together with the control and protection strategies and the components that we need to build and control and protect offshore HVDC networks. Based on this, we have developed recommendations for how to specify and implement these strategies and how to validate their performance both technically and economically. We have also verified the compatibility of different types of technologies and the extent to which they can be integrated into a functioning HVDC system. We have developed definitions for common interfaces. We have created common specifications and test requirements to support interoperability between equipment from different vendors. We carried out a gap analysis of the legal and regulatory frameworks in the North Sea to propose solutions for differences and formulate a clear set of recommendations for regulators, policymakers, and politicians. We modeled the offshore wind generation scenarios in order to derive the potential types of network topologies that can result, which allowed us to calculate the costs and the benefits and find out which approach would be best. And finally, we have demonstrated that the key technologies that are necessary to build meshed HVDC grids are ready for real-world application in pilot projects. So we tested HVDC grid control, HVDC grid protection, HVDC circuit breakers, and of course the topic of today, HVDC gas-insulated systems. We showed that the TRL, we improved the TRL of these technologies to a level where we think they are ready for real-world application in a pilot. So to conclude, based on the work done in promotion, we believe the technology is really ready for the first steps in multi-terminal HVDC grid development, but that we need significant amounts of standardization work to be done still. And that one of the key first steps are, on the first hand, improved and stronger international collaboration and coordination, and a full-scale pilot project, which we need to demonstrate not only the technical feasibility, but also that multi-terminal grid realizations can really increase the benefits to the European consumer. So we were a project of 34 partners over 4.5 years from 11 different countries with a total budget of 42 million euros, of which 34 was funded by the EU and the rest by the partners themselves. And as you can see, our partners covered the full value chain for offshore HVDC grids, ranging from TSOs to manufacturers, universities, consultancies, offshore wind developers, testing laboratories, and research institutes and industry associations. So if you're interested in any of the results, most of the deliverables that we have are publicly available on this website here, where you can go into a lot more detail than what I could just tell you in this already too long presentation. So thank you for your attention. And with this, I hand over to Uwe, right?
Hello, Uwe. Can you hear us?
Yes, of course.
Ah, there is.
There are some problems with others to connect to our session. So can you see my screen already?
Yes, looking good.
Yeah. So yeah, thank you, Case, for the introduction. And now I will pick up one of the topics you mentioned and focus on a Hvdc gas-insulated switchgear. If you compare an AC switchgear, a gas-insulated switchgear with an DC-insulated gas-insulated switchgear, then you will see that a Hvdc Gis installation can be built with a much higher degree of compactness. and a significantly lower sensitivity to ambient factors. And that is known from AC side, and that is the same also for a DC. And based on that, as the most obvious cost-saving potential can be found on offshore converter platforms, of course, where the required air clearance for an air-insulated substation leads to much larger and heavier offshore structures. So summarizing, it can be said that by using a Hvdc GIS, the volumetric space of a switchgear installation can be reduced by 70 to 95%, depending on the design of the Hvdc platform. Looking to the components we need for a Hvdc GIS, so that is very similar to an AC GIS. You could see here one picture of the typical components, which is very similar from the different manufacturers of a Hvdc GIS. So starting from the right side, we have a connection between GIS and air, so the bushing from gas to air. Going from right to the left, we have a disconnector and earthing switches, connecting elements, and surge arrestor, voltage and current measurement devices. So normally for a DC GIS, an RC divider is used for a voltage measurement, and the zero flux principle is used for a current measurement. And on the left side, you could see an cable termination, so a connection from a GIS directly to an Hvdc cable. And moreover, we need also a diagnostic and monitoring tools very similar to an AC GIS. I have to mention here also that we do not talk about a circuit breaker. That's a different story, but that was also part of the promotion project. So if you want to know more about the Hvdc circuit breakers, then you can check the web page from promotion, and there you will find a lot of material about Hvdc circuit breaker. But going more into the details for an Hvdc gas insulated systems, so looking to all problems or issues we have to cover. The first thing is, of course, the technology. That is what you see here on the left. So the field distribution in an Hvdc systems is completely different compared to an AC systems. So here the resistivity of the different materials is of higher importance. Therefore, we have an influence of temperature and also of the electrical field itself on the field distribution inside the system. That means that the DC field is not constant, in contrast to the DC voltage, which is very constant over time. Second thing is the equipment itself. I talked already about a little bit this different equipment that looks very similar to an AC system from outside, but of course, due to the different field distribution, we need also special insulators. So all kind of solid insulators are completely different to an AC systems. Talking about experiences, so up to now there is not so much experience. We have 1 or 2 substations in the world operating under DC voltages. That's completely different to the AC GIS. Of course, different dielectric field distributions need also an adaptation of testing. And here it is to say that up to now we do not have any standards for a DC GIS. Another topic is monitoring and diagnostics. So can we use the same techniques we are using for AC systems, or do we have to adapt these systems? And another topic is, of course, the eco-friendly design. So here we are talking mainly about different gases or a replacement, possible replacement of SF6. Now, focusing on promotion, we have tried to cover most of these topics, and we have managed that in different task groups. The one group was dealing with the specification of a DC GIS and with long-term testing requirements. The second task group was established to develop monitoring and diagnostic methods, and also to discuss the possible replacement of SF6. The third task group was established to prepare and to run a long-term test of Hvdc Gis equipment for 320 kV. And the last fourth task group was initiated to talk with the standardization and to initiate standardization activities for Hvdc Gis. Of course, that was done in strong cooperation with CGRE and IEC. I want to mention also which companies were involved in the WorkPackage 15. So from utility side, we had Scottish Power, Sheet Transmission, and TenneT. From lab side, that was KEMA Labs and DNVGL from the Netherlands. From manufacturer side, Hitachi ABB, and from the research side, the High Voltage Institute of the Technical University of Delft and the Supergrid Institute in France. And also for the workshop today, we have tried to follow this structure. So we have today 3 sessions. The first session deals with the technology and dielectric testing. So here we have one presentation from a manufacturer from Japan and a second presentation from a Hvdc long-term test for an Hvdc GIL. And moreover, we have 2 presentations from the WorkPackage 15. And the second part of this session, we are focusing on the application and on standardization. Here we have 2 presentations from transmission system operators, from 2 utilities, from 50 Hz and from TenneT. And moreover, 2 presentations from 2 different CGRE working groups dealing with Hvdc GIS or with cable connections, and 1 presentation from an running IEC group about Hvdc switchgear. And in the third session in the afternoon today, we will focus on diagnostics and on new gases. Here we have 1 presentation from a running CGRE working group and 2 presentations from the WorkPackage 15. Before I want to hand over to the chairperson of the first session, I will shortly introduce the session chairs. So for the first session, Michael Gatche will go through the session. Michael is with Hitachi ABB Power Grids, and he works as a senior engineer for gas-insulated switchgear. And in WorkPackage 15, he was a task leader for the standardization task group. The second session will be led by Nadu Belda. He is from KEMA Labs and works there as an innovation engineer. He was also a task leader in WorkPackage 15, but he was also responsible for a work package dealing with Hvdc testing of Hvdc circuit breaker. And this last session after the lunch break will be led by Armando Rodrigo Moore. He is from Delft University and works there as a lecturer in electrical engineering and at the same time also at the University of Valencia. Yeah, that is all from my side, and I will directly hand over to Michael Gatche, who will chair the first session, the first technical session.
Yes, Uwe, thank you very much for the kind introduction. And also from my side, warm welcome to everyone to the first session on technology and dielectric testing. We are really looking forward to this session because we have some very interesting presentations on Hvdc GIS in Japan, testing of Hvdc GIS, Hvdc GIS prototype installation test, and Hvdc GIL prototype installation test. And the first presentation will be Hvdc GIS in Japan by Yoshima Sato. He is with Toshiba Energy Systems and Solution Corporation. He has a master's degree from Tokyo Institute of Technology and started working with Toshiba in 1994. The focus of his work was transmission and distribution engineering, and especially in the last year with a special focus on engineering of power electronic systems. He's member of the Institute of Electrical Engineers of Japan, as well as IEC TC 115 Working Group 5. And yes, with this short introduction, I think we can start with the first presentation. Just want to remind everyone that during the presentations, if you have any questions, please type them into the chat. We will go through all the 4 presentations in one go. And afterwards, we have time for a longer discussion session where we will be able to discuss all the 4 presentations. But we would go through all of them in one go and then come to the questions. But if you have any questions, just post them into the chat during the presentations. And with this, I would like to start with the first presentation. So Sato-san, I kindly ask you to take over the screen and start with your presentation.
Can you hear me?
We can hear you, yes.
Okay, so wait for a moment. And can you see my presentation file?
Yes, we can see.
Okay, so let's start. Okay, good morning and good afternoon, everyone. I'm Yoshima Sato from Toshiba Energy Systems Solutions Corporation, Japan. It's a great pleasure for me to introduce you Hvdc Gis in Japan. I hope my presentation would be helpful for the activation of today's discussion in this workshop. These are today's contents. First one is background of Hvdc Gis development in Japan. And secondly and thirdly, I will introduce outline of the first and the second Hvdc Gis development. And the next, I will suggest a future prospect of next Hvdc Gis development, and lastly, conclusion. So the first one is background of Hvdc Gis development in Japan. You can find the map of Japan on the left side of the page. Japan is a typical island country and surrounded by the sea. And you can find also from the map available flat area, it means which colored in light blue or green, is quite small because around 70% of the land is mountain area. In addition, most of the flat areas are very close to the sea, and the salt pollution is quite severe. For example, many typhoons come to Japan every summer and autumn, and they bring some salty atmosphere. Then, compact and highly environmental resistant GIS is strongly required in Japan. And this requirement is quite similar to that for offshore platform because of its limitation for space and also environmental severity. I added on the map some points, and you can find some HVDC link in Japan and also some converter stations. As you know, Japan is the only one country which have both 50 Hz and 60 Hz as commercial frequency. So we need some frequency converter stations. And another one is showing the back-to-back converter station, which contribute well-controlled power flow in AC grid. So the first GIS which developed in Japan is used for HVAC power grid, as same as other country did. And the number of HVAC GIS have been operated well since late 1960s. And the point is, many of these GIS were installed outside because it is difficult for us to keep some areas for the building for GIS. And in 2000, the first Hvdc GIS, the key channel Hvdc link, which locates here, western side of Japan, started its commercial operation. So at that time, we had more than 30 years experience of GIS operation. So these experiences are quite useful for the first Hvdc GIS development. And in 2019, The second HVDC GIS, which is applied to the new Hokkaido Honshu HVDC link, which locates here, started its commercial operation. So during around 20 years from the first HVDC GIS, we carried out a variety of investigations and experiments. Later I will introduce. In this page, I showed main specification of each HVDC GIS. I don't explain one by one, but the point is most of these specifications were defined project by project because at the time no common standard had not yet established. So from this page, I would like to introduce outline of the first Hvdc GIS development. The picture shows the first Hvdc GIS which installed at Annan converter station of the key channel HVDC link. For this link, future DC 500 kV operation is taken into account. So DC 250 kV GIS and DC 500 kV GIS were installed. Now it's being operated at 250 kV DC. And in order to realize the facility compact, DCG zinc oxide arrestor was improved to reduce LIWV, lightning impulse withstand voltage. And also, field verification test was carried out before the products were installed for around 1 year because it is the first experience for the Hvdc GIS for Japan. And in this page, I picked up some Hvdc GIS technological knowledge at the time. The first one is quite well known. SFC gas shows quite high electric strength, but is quite sensitive against metallic particle under AC application. It's based on a lot of HVAC GIS experiences. And the second one is important. Firefly phenomena can occur under negative polarity DC application. And at that time, it was considered that firefly phenomena will persist once it starts. And next one is charge accumulation insulating spacer was also considered. So this knowledge is quite useful for the first development of Hvdc GIS, but in other words, somewhat qualitative knowledge compared with the latest knowledge in Japan. And in consideration of such knowledge, we defined the main points of HVDC development. At first, we defined that maximum length of metallic particle is 3 millimeters, and no breakdown by LIWV, even under firefly condition. And also no breakdown by LIWV, even if the metallic particle is attached on the weakest point of the insulating spacer. In order to realize such required condition, particle traps are arranged on the high voltage conductor and the grounded metal enclosure in order to make metallic particle harmless. And also coating is arranged on the inner surface of the grounded metal enclosure. And next is outline of the second Hvdc GIS development. The picture shows the second Hvdc GIS in 2019 at Hokuto converter station of the new Hokkaido Honshu HVDC link. In this link, a symmetrical monopole system is applied. And the point is, insulation material of this link was changed from that of the key channel HVDC link. And also the coating material on the inner surface of grounded enclosure was changed. So at this moment, it is difficult for metallic particle to lift off. From this page, I would like to introduce some sample of our investigation and experiments. we prepared some model of Hvdc Gis busbar, and we used high-speed video camera, and we took the movie. And the right side, we showed the picture of the picture of the shot of the movie. So you can maybe find the metallic particle lifting off and the fire flying, and sometimes we could observe partial discharge. And also we checked duration of the firefly. So at the lower figures, we showed the summarize of the result, and you can find maybe in the left side of the figure 4 lines there, and for example, one is 3 millimeters of the length of metallic particle under 1 PUDC application, and also another one is 2 millimeters of metallic particle under 1 PUDC application, and they are clearly identified each other. So we convinced that duration of firefly depends on the metallic particle length. And next is the investigation of effects of particle trap. We prepared also busbar model of this GIS, like as photo shows, and also we used high-speed video camera, and we took movies through the glass observation window at the end of the busbar. And inside of the enclosure, we put some metallic particle rockets here, and we applied negative and positive DC to the high voltage conductor. And we observed that at the high voltage side trap, fire flying particle easily falls into the grounded to enclosure side trap, and under normal operating voltage, and it will never lift up again because of the low electric field there. And this figure shows the final location of the metallic particle after the DC positive and negative application. So the circle shows the shape of grounded side trap, and also this shape shows the high voltage side trap. It means the conductor. So the location of the metallic particle is pointed on the picture. So you can see no metallic particle could reach insulating spacer. Left side is the side where we put metallic particles, and the right side is the spacer side, and no particle could reach insulating spacer beyond the traps. So it is quite useful. And also we performed surface charge measurement test. We prepared silicon dioxide filled epoxy like the photo shows, and we observed the accumulated charge on the surface of the spacer. So upper side is under ambient temperature, and the lower side is with temperature gradient between the electrode of the center of the epoxy and the perimeter part of the epoxy. So finally, we found that accumulated charge distribution on surface, and this accumulated charge intensified the tangential electric field by about 20%, but it was significantly lower than surface flashover level. So from this page, I would like to suggest future prospect of next Hvdc Gis development. As I previously explained, based on the review of Hvdc Gis in Japan, we think the following 2 points are main keys to next step for Hvdc Gis development. The first one is further improvement of metallic particle control. For example, particle trap arrangement, coating on the inner surface of grounded enclosure, or high voltage conductor design. And the second one is further modification of insulating spacer, taking into account charge accumulation to insulating spacer. Of course, we will continue insulating material development, but also further accuracy improvement of electric field strength simulation will be required because the influence of the accumulated particle is quite sensitive. So further accuracy will be required. And the last but not least, these 2 points may trade off other design factors inside the DCGIS. Therefore, coordinating engineering would be requested also. Okay, so conclusion. The first and second Hvdc GIS in Japan were reviewed in this presentation. The first Hvdc GIS was developed taking into account firefly phenomena and charge accumulation to insulating material, but in other words, somewhat qualitative compared with the latest knowledge. And the second Hvdc GIS was developed based on the investigated fact that the duration of firefly depends on the metallic particle length, and also intensified tangential electric field strength was measured and proved to be lower than expected field strength. And finally, I suggested the further improvement of metallic particle control and modification of insulating spacer, taking into account its charging, are keys to the next step of Hvdc GIS development. And also, coordination between these points and other design factors would be required. That's all of my presentation. Many thanks for your kind attention. Thank you very much.
Dear Sato-san, thank you very much for this very interesting presentation. I already see also the first questions coming in. So I will collect them all. And again, I encourage everyone to post more questions, and we will go to them after the session. Right now, we will continue with the next presentation, which is testing of Hvdc GIS. The presentation was prepared by Nadu Belda from Kema Labs and Hong He from DNVGL Netherlands. Nadu will present. He is an innovation engineer at Kema Labs since 2015. And his work is especially focused on the development of test methods and the design and implementation of test circuits for HVDC switchgear. And especially within the promotion project, one highlight was the testing of several HVDC circuit breakers. And yeah, with this short introduction, I gladly hand over to you, Nadu. We look forward to your presentation. We cannot hear you yet. Please unmute. We can see the presentation, but not hear you.
Sorry for that. I thought I unmuted it. Thank you, Michael, for the introduction. And good morning, good afternoon, and good evening, maybe to some of you. Well, I will be talking about the testing of 320 kV Hbdc GIS that we have performed in our laboratory. Well, Michael has introduced myself very well, so maybe I just mention my name. My name is Nadu Belda. I'm innovation engineer at Kema Labs. Kema Labs is now part of a JC group. Well, I was active in promoting project, of course, not only in this work package, but also in other work packages, work package 5 and 10, where we focus on testing of HVDC circuit breakers. I guess you will find more information on project website. Today, of course, I will be talking about the testing of HVDC GIS in our laboratory. Well, the content of my presentation is as follows. Well, I will give you a brief introduction of what a prototype installation testing is. Of course, it is not a specific component test. So you see the photo of the GIS in our laboratory, a small photo on the right side, and then try to describe what was included in the test equipment as a whole, of course. Which test program did we follow and what are the results, just to give you some information about the achievements within the project. Maybe coming to the prototype installation test, of course, there are different types of tests, and prototype installation test is a kind of unique and special test. Other tests, for example, it could be development test, where the focus is the use of an equipment for a new or a special service, for example, or new development, which is normally performed at manufacturer. And the type test performed at independent laboratory, which is focusing on verifying the rating of specified equipment. And then there is a routine test, which makes sure there are no anomalies in the manufacturing process of a specific product. And then, of course, there is on-site test, which makes sure that an equipment which is installed in service is ready and up for running. So that's kind of commissioning. And then the prototype installation test, which is basically the whole GIS installed as it would be in service. So it's a full-scale GIS, and the test itself is special in a way that it is not a short time test. This is a long duration test which lasted more than 1 year, basically in a laboratory, applying different types of tests. And in this test, all the representative stresses, as it would be in service, is applied: electrical, thermal, and also mechanical. Then, of course, the main purpose is to increase the technology readiness level of Hvdc Gis, which, of course, I think in many parts of the presentation during this workshop will be mentioned, has been increased to a technology readiness level of 8 for this case. And of course, the test is not only verifying a rating of a specific component, it is the whole process, actually. The production is involved. And then, of course, installation and commissioning, because it would be, as I said, installed as it would be in service, actually, with all the components, all the monitoring on board. And we try to mimic a long-term service condition, actually, operation for decades. Well, the test object itself is SF6 field, gas-insulated systems for Hbdc. Here you see a photo of such of the test object, actually, from our laboratory. Well, this will be explained later by Michael in detail, of course. Just to give you some information here, the total length of about 31 meters of bus bar is involved here, including different shapes, straight, L, T, and X shapes. And it has been divided into 8 partitions. Each partition is, of course, has partition insulators. So that means 8 of them are involved, and there are lots of support insulators. Here you see the bushing of the DC GIS. One of the bushing is connected to the DC source. And there is an extension bushing on the right side, which is kind of optional in case it is needed. And then, of course, we have to apply current into running in the bus bar. That means it must be applied through current transformers. We have used AC sources for this purpose, so equivalent AC current has been running through the bus bar. This has been applied through these 3 current transformers, conventional current transformers. There are also measurement equipment on board, current sensor. They call it zero flux current sensor, which can measure AC and DC. There is also a divider, RC divider on board, as you see it here. And there are also switching equipments, disconnectors, 3 disconnector and earthing switch. There is a fast earthing switch in this location. And of course, many other monitoring measurements, for example, gas density, partial discharge monitoring on board was also available. Different technologies have been used, arc detection, and also temperature monitoring of the enclosure has been included. Well, just to give you a highlight, the single line diagram of that GIS you just saw looks like here. So with all the disconnectors and all the components. And the rating, the nominal voltage of the Hvdc Gis is 320 kV, and of course we have that is for continuous rated voltage of 350 kV. And of course, it has been specified what lightning impulse voltage we apply, what switching voltage we apply. I think the background, Michael will give you how it was specified, where it is coming from. And we have applied also not only the impulse itself, but superimposed impulse on top of the DC voltage. The whole GIS is rated for 4,000 amps of current DC, and there are also short time currents with standard specification. Here you see 64 Ka, for example, for 1 second, and the operation range between -30 to 40 degrees Celsius. The test program, of course, as I mentioned, it is a prototype installation as it will be in service. That means there are lots of procedures. The first one is a pre-test. A pre-test is that, of course, to make sure the installation is correct, everything is correctly installed. Then check if it is ready for running. That means the thermal cycle by applying current through the bus bar, and also applying impulses, lightning and switching impulses, partial discharge measurement before the start to make sure everything is okay. Also superimposed impulse application, both lightning and switching impulse have been applied on top of DC, and also application of a DC voltage for each polarity for 2 hours positive polarity, and after 2 minutes we change polarity again, and for negative polarity another 2 hours, and reverse back to positive for 45 minutes. Once we make sure everything is okay, then the test, the long term itself starts. This long term test is divided into different testing blocks, 6 testing blocks. Each testing block lasts for 60 days, as you see it here. These blocks are at different loading conditions. That means there is a zero loading, which means there is no current flowing through the bus bar, but only a voltage applied to the system. And there is high load. At high load, 4,000 amps of current is running through the bus bar. And then, of course, we change polarity at each testing block. So one testing block at positive polarity for 60 days, and then we reverse at different loading. In between each testing blocks, of course, we apply superimposed impulses, both lightning and switching, and also close open operations of the disconnectors and earthing switch. And AC partial discharge measurements is performed to monitor the condition. And this, as you see, it takes, of course, the 1 full year for just on the long-term test, and that is followed by a load cycle. In reality, the current is not either zero or full rated value, but it varies depending on the power flow in the system. So we try to mimic that with a load cycle, where sometimes of some hours of the day it is fully loaded or reduced, or maybe less loaded. So this has been performed for the 2 polarities, each polarity lasting for 15 days. I come back to this later. And then, of course, subsequent tests, which means after finishing the whole test, we check if everything is okay, if everything is intact, by applying different measurements, different impulses. And that's also followed by visual inspection after dismantling of the test object. Yes, just a few words about the monitoring system. Of course, we have used lots of monitoring, most of them from the manufacturer, also from our side. We do measurements of voltage and current and record them, of course. Here you see on the right side the measurement of temperature, surface temperature of the enclosure. We have put 15 thermocouples at the most locations which we thought would be hotspots. And of course, there are also monitoring of ambient temperature. That's why we place thermocouples in the vicinity of the GIS to control the room temperature also. And then, of course, as I mentioned, there are inside of the GIS, there are gas pressure measurements, partial discharge monitoring, and also arc detection. And here you see we check, of course, the switch from the switch panel, the position of the disconnector and ending switch, so that can also be controlled. So everything is recorded in our system. Just to show you some load, the three types of load I mentioned. Here you see the high load, just one specific day for 24 hours measurement you see here. On the left side of this graph, you see the temperature measurement. On the right side, you see voltage and current depending on the color. So we also monitor the ambient temperature. You see it is the ambient temperature. And at high load, as I said, we apply 4,000 amps of current through the bus bar. That means there will be heating, which will transfer to the enclosure. And that is what you see the temperature of the enclosure in this one. About 20 degrees Celsius difference we could see during the high load. This is one specific day, of course. There is a zero load. In the zero load, there will be no current flowing through the bus bar. That's why you see it here, zero current measurement. That means there is no heating in the system, which means the surface temperature will be the same as the ambient temperature here. And of course, we apply the voltage of 4,200 volts, which is basically higher than 350 kV. I believe Michael will explain this in detail later. Of course, we have applied 20% more than the rated continuous voltage to take into account some aging aspects as well. The load cycle I was mentioning, which is more realistic, as I say, the power flow in the system changes during the day, of course. This is typical day where at some hours of the day it's fully loaded, and in some cases it's really low loaded. So that's why you see also the enclosure temperature following the loading of the bus bars. Just a few words about the test results. Here on top of the diagram you see is the test setup that we used, and also the photo of the whole test setup with all the components actually. So we have a DC source on the left side, you see it here, and impulse generator on the right side of that photo, and also measurement spark up. We have used spark up for applying superimposed lightning and switching impulses. On the left side, you see the actual measurement of superimposed switching and lightning impulses. On the most left, you see the lightning impulse superimposed onto 350 kV DC, both for both polarities. And next to that, you see the switching impulse superimposed onto the DC voltage again for both polarities. Well, just to give you, this is a photo of on one of the days where people, different stakeholders, are invited to witness the testing. This was performed in combination with a demonstration of DC circuit breakers. Of course, the difference here is for DC GIS, you don't see much activity. You don't hear actually. Maybe you see a lot of dust as you see it here, of course, a little bit behind. But people were invited to see the ongoing tests, of course, many times, not only in this occasion. So just to summarize, of course, at this time, promotion is finished. The test has been successfully completed. All the test program is finished, as I mentioned, the pre-test, checking everything, and also the long-term test divided into 6 blocks plus 2 load cycles. This was also successful, and of course, in between the checking of partial discharges and all the monitoring has been performed. And subsequent tests, of course, as I said, we apply impulses, we open the disconnectors and also apply impulses, switching impulses, lightning impulses there to make sure they are fine after more than a year under stress. And of course, we try to, after opening, we try to check visually if everything is okay. And actually, I thought maybe it's nice for you to also see what is inside of the Hvdc Gis. Well, we have dismantled, as I said, it is followed by a visual inspection. We see when the manufacturer is dismantling it. Here you see the corona ring taken off the DC bushing. As I said, one of the problems was the dust, of course, even if it was cleaned so many times. I mean, the whole room, but it's still there. That's one of the challenges. Inside of that bushing, you see the conductor and, of course, the enclosure, which that is after, of course, taking out the gas, the SF6 gas. Another view from a different direction. You see it here. Well, maybe a bit more closer view here. You see, you can see support insulators and also the conductor itself. And here is the partition, one of the partition insulators. As I said, it is 8 compartments, and the 8 compartments are divided with these partition insulators. So that's all I wanted to say. Thank you very much. Please feel free to ask questions.
Nadu, thank you very much for the presentation. Again, I encourage everyone put the questions into the chat, and yeah, we will come to it in the discussion session. And yeah, I think there couldn't have been a better introduction to my presentation than your presentation, Nadu. So thanks very much. I will take over with the title Hvdc GIS prototype installation. How does it increase technology readiness? So we've now seen the details of the test. I will speak a bit more about what's the role of this test and the prototype installation itself, and how does it help in the frame of the promotion project to increase the technology readiness level. You can see the screen.
You're not sharing it yet.
Okay, then I'll start sharing. That's probably a good idea.
Yeah.
1 second. Okay, there we go. Okay, so now you can see the screen, I guess. Can you?
Yes.
Okay, great. Then, yes, the presentation, how does it increase technology readiness? So I will start with a short introduction about the role of the prototype installation test, about the specification and the rating of the test poll, how we came up with this in the WorkPackage 15. Then a few words about the installation and the test itself. I mean, Nadu, you have given the main presentation, so only a few key points. And then after the test, how is the technology readiness for Hvdc GIS now reviewed after this test? And yeah, so let's start right away with the role of the prototype installation test. So how does it go when we develop a new product as a manufacturer? So usually we start by doing basically the R&D cycle, doing simulations, doing development tests. And at the end of the R&D, we want to have a reliable product that can be operated for several decades. And what is usually done for an established technology like Hvgis for AC application is we perform all the type tests that are necessary for the product, dielectric, switching, mechanical type tests. And then we also perform, once everything is type tested, the project-specific routine tests to ensure the quality of production in the factory, but also to verify that on-site, on the project side, everything is assembled correctly. However, for a new technology like Hvdc GIS, the technology readiness level would be evaluated a bit lower than like for an established technology. So out of the 9 technology readiness level, at the start of the promotion project, we would have evaluated Hvdc GIS at level 6 out of 9. So there are some type tests, or at least recommendations for type tests, for example, from the SIGRE pre-standardization work, where we have DC-specific type tests added, like superimposed voltage testing or the insulation system test that combines dielectric and thermal stresses. But there's still also from let's say the user side and from the operational experience side somehow a gap between these type tests and the reliable operation in the field. And what we try to do within promotion is to bridge this gap from the, let's say, somewhat lower technology readiness level to the real-world application by means of a prototype installation test. And this is basically a full-scale demonstration that includes not just the testing, but also the specification and the engineering of an Hvdc GIS, like it would be done in a real project. It also contains the installation and the commissioning of a large test pole on site. It includes long-term testing with representative stresses for more than 1 year. And also the test pole includes not just, let's say, the primary technology, but also monitoring and diagnostic systems. And we have basically during all the steps third-party examination. As we already saw in Nadu's presentation, we have it during the test and we also have it after the test in the visual inspection. And the purpose of this test is to verify the overall performance of a manufacturer to be able to deliver an Hvdc GIS of the investigated voltage level. It is not a mandatory test like a type test. So it's also not to be repeated when you have a small design change in the technology or in the product. And what we should also keep in mind, and I think that also came out from Nadu's presentation of the steps in the test, the prototype installation test is not the combination of all the type tests, so not a combination of all the worst cases, but rather it is, let's say, a simulation of real in-service conditions that are, of course, somewhat harsher than a normal operation because it cannot run for 40 years, so we have a bit of increased voltage. But it is should be typical for real in-service stresses or for combined stresses. So the first step is the specification and rating. So in the WorkPackage 15 in promotion, how did we come up with specification and ratings for Hvdc GIS? The specification was done on the example of 3-terminal 320 kV Hvdc offshore hub. The example that was used there was a connection from Shetland to Scotland. It is an Hvdc link where we have basically in the middle of the link added an offshore wind farm that should be connected to the link, and so there we should have a 3-terminal Hvdc hub to connect this offshore wind. And in this deliverable D15.1 that I've also linked here, you can read more details in the document there. There we had some specifications what an Hvdc GIS must be capable to be able to be used in this offshore hub. And as a manufacturer, we then came up with ratings that cover these specifications, and in some cases also slightly surpass them. But the GIS would be capable of handling these specifications. And the rating that was used was a 320 kV Hvdc GIS with a rated voltage of 350 kV DC. We have a lightning impulse level of 1050 and a switching impulse level of 950. All of this, of course, also superimposed with the rated DC voltage. We have a rated DC withstand voltage to earth of 610 kV and 4000 amps rated current. And it can be operated in an ambient temperature range of -30 till +40. Yeah, you've seen the picture of the test pole also already from Nadu. It has the form of a ring, and it has 2 SF62 air bushings to connect to high voltage. The second bushing was used for the subsequent test, where we also tested the withstand of the disconnector in isolating distance. And to be able to heat up the test pole, we had conventional heating current transformers to drive a current of the rated current 4000 amps through the ring for long times, and to be able to also operate it at elevated temperatures. Basically, the ring contains necessary components to construct a typical HVDC substation. We have different shaped elements. We have dismantling units. We have switching devices, disconnector and combined disconnector and earthing switches. We have fast-acting earthing switch. We can measure DC current and DC voltage with the GIS instrument transformers and RC divider and the zero flux sensor for the current that is also capable of measuring AC. And we had partition and support insulators. So although we have quite a lot of components, we had 8 compartments because we also used the partition insulator. The support insulator, sorry. And as an additional solid insulating material, we had also the insulating rod of the disconnector and earthing switches in there during the whole test to also test them for the full voltage. And the pole is also equipped with monitoring systems, which, let's say, typical monitoring systems that would be used in a real installation, and also with a few more experimental systems. So we had the gas density monitoring, we had to monitor PD activity, we had the UHF system, but also an optical system, HFCT system, and a magnetic antenna. I think here, especially about the more experimental systems, we will hear more in the third session by the promotion partners that worked on that. We had arc detection and enclosure temperature measurement throughout the test. And what you can see here is now a time-lapse video of the installation and commissioning on site in Arnhem. You can see we start with the steel supports, and then all the factory modules arrive and are connected together to form the ring. Here, of course, the cleanliness is observed by the installation team. And you see how the ring is building up. After that, the crane comes in and connects the bushing and the RC divider. And after that, we connect all the secondary technology. And then it's time for the commissioning test, which is done with an AC resonance system. And yeah, after that was successful, the test pool was ready to start the main test. Here, just a short recap. Nadu has told it in more details. We had these 8 blocks with varying voltage and current load. All the blocks were terminated with the superimposed voltage. And in total, we can say we had more than 390 days of DC voltage of 120% rated DC voltage, so 420 kV all the time. And mid of last year, we completed the test successfully. And more details for the test program can, of course, also be found in the D15.2 deliverable document that's also publicly available on the promotion website. So, of course, if anyone's interested in more details there, I encourage you strongly to go to the website and look it up there. So after we've done the specification, installation, and the testing, how is the technology readiness of HVDC GIS assessed? And here I borrow some input from the promotion colleagues of WorkPackage 12. WorkPackage 12 was a key work package because a key deliverable was the deployment plan for a future European offshore grid. And part of this work package was the 12.A, which is basically a technology readiness review for key technologies that we need for a meshed offshore HVDC grid. And here the HVDC GIS system with SF6 was also assessed. And what you can see is that before the test, before promotion, we have assessed this as a level 6 out of 9. So basically, technology with the type tests, we say that technology is demonstrated in an industrial environment. And what we've done then in promotion, we have worked to get recommendations to specify an HVDC GIS and also to long-term test an HVDC GIS. This is already a first increase. And then we have done the long-term prototype installation test, including the installation and everything. And with this, we have now a technology readiness level of 8 for the complete system HVDC GIS. So basically, this is the highest level that you can reach, I would say, in a lab. And the next step is then really an on-site and real world service of the technology. To summarize all of this, we did the prototype installation and promotion with the type-tested 320 kV Hvdc GIS design. We had all the major components included. We had a realistic size of the test pool, and we had a customer project-like execution of the project, including the specification, the engineering, factory production, routine tests, on-site installation and commissioning. Then the test was successfully performed according to the recommendations of SIGRE and also promotion as a prototype installation test, third-party inspections throughout, and the test was successfully finished. And based on this, the technology readiness level for this compact Hvdc GIS is now assessed as level 8 out of 9, so system complete and qualified. And with this, the next step is really the real-life operation in the grid on an offshore platform. Yeah, with this, I would like to end my presentation. I thank you all for the attention. Again, please feel free to post any questions. And yeah, with this, we come actually to the when I can leave the presentation here, we can we actually come to the next presentation, and the next presentation will be held by Martin Hallas from Technical University of Darmstadt. It is about an Hvdc GIL, so the gas-insulated line prototype installation test. And Martin is a researcher in gas-insulated HVDC systems. He is responsible for the 550 kV HVDC test facility of TU Darmstadt, and he's project manager especially for the long-term testing of Hvdc GIL. And yeah, with this, I gladly hand over to you, Martin. We're looking forward to your presentation.
Okay, thank you very much for the introduction. Do you hear me?
Yes, we can hear you.
Okay, do you see the slides?
Yes.
Okay, great. Okay, yeah, thank you very much for the introduction, and also thank you very much for giving the opportunity to show our project here. So we are actually not related to the promotion project. We have a separate project, Hvdc GIL prototype installation test at our university in Darmstadt. We are also state funded from the European Union, and our project is in cooperation with Siemens Energy. So I would like to share, first of all, a little bit of history of our project. So we started in 2015 here at an area in Griesheim near the city of Darmstadt. And as you can see, there's nothing on this area, there's just some forest. So the first step in our project was to clear the forest. And this is a quite big area, it's around 10,000 square meters. And this was performed in 2016. Then the first construction was started in this area in 2017. And in 2018, we could build the high voltage laboratory, which was required to include all the test equipment for the test. And then in 2019, the Hvdc GIL assemblies were built in the test facility. Here you see the one test assembly which goes outside. We have a second test assembly which is directly buried in the ground, which has tested the thermomechanical behavior of the Hvdc GIL. I will not deal with this assembly today. I will focus on the assembly marked here on this slide, which is to analyze the thermoelectrical behavior of the Hvdc GIL, and again regarding similar to this prototype installation test. So this slide I can jump over a little bit faster because there was already a lot of stuff told. We are also performing a prototype installation test according SIGRE. Again, to remember, it's a 1-year long-term test on the Hvdc GIL, and we perform simultaneous DC voltage and DC current stresses, and also we perform periodic overvoltage stresses on the device under test. And as Michael has explained it very nice, it's also again a proof of the DC GIL technology, and also similar to later customer application, which means also this assembly was built at on-site conditions. And here on this slide, you see what was actually be built. So we have an DC GIL assembly, which is 50 meters in one direction and 50 meters in the other direction. So in total, 100 meters. So at picture number 2, you see the DC GIL assemblies in line. Picture number 3, you see that there is the connection points. So here are GIL and GIS parts mixed together to create the overall assembly. Generally speaking, also here, all major modules and insulator components are included in this assembly. So to cover all assemblies. And here on the bottom, you see the test facility in the high voltage hall. And my presentation will actually focus on this picture here and on the test equipment installed here inside and how does it work and why we have done it like that and not differently. I will not focus on DC GIL technology. I mean, when you talk about projects where you need DC GIS, of course, you also need some pipe modules to, also transmit power for that, for example. So here you see more into details, the view in the high voltage laboratory. So we also have a DC voltage source, which is generating the high DC voltage. It's connected to this single bushing here, and this bushing then feeds the DC voltage inside the GIL. We also have an impulse voltage generator to investigate the overvoltage behavior of the assembly. For that, we are not using conventional lightning and switching impulse. We are using oscillating impulses. I will explain this later on. To put the overvoltages to the DC voltage. So this is a superimposed voltage test. You have a continuous DC voltage and you want to connect, while you still are applying DC voltage, you want to connect the overvoltage. For that, we apply a spark gap. I will also explain this, why we have done this. And to analyze this thermoelectrical behavior, so the space charges which are accumulating, volume and surface charges and so on, you need a current. And as we have heard, you can use an AC current to heat the overall assembly. We are using a different approach. We are using a DC current. And this source here, which is shown here on the left side, is a novel generator, which was built and developed at our university. Our main measuring components are here, an RC divider and also a zero flux current transformer to measure the current and to measure the voltage with the RC divider. So why did we have chosen DC current? So our goal is 3050 amps at 660 kV DC. And when you keep in mind that we have 100-meter loop, you have to consider that an AC current also will need some reactive power. And when you check now the numbers for AC current and DC current, you will see that an AC current heating for our loop would need in the range of 150 kilovolts amps reactive. So you need test generators with this rating. So a lot of current transformers inside the loop. On the other side, as active power you only need for this long loop, 10 kilowatts. This is not very much. So you see it's a very efficient solution to use DC current to heat the inner conductor. And what else comes with this, when you choose DC current, that you also directly apply the same current stress as you have it for the later operation in the grid. And so mainly because of first argument, there was the decision in the project to follow the step and to design such a DC current generator and to build such novel generator up. And here you see the overall generator. I will try to explain the concept in principle now. So we use in principle capacitors, which are shown here, and capacitors are ideal to separate the high DC voltage from earth potential. So this is the first thing which has to be done. You cannot just directly plug it into the power supply. You need some isolation between the plug-in for the rectifier from high voltage to earth, and this is done via the capacitors which separate the high DC voltage. And on the other side, you know that capacitors have a lower impedance when you increase the frequency, and this you can use when you put an AC-AC converter on earth potential, which generates a high frequency current. We are using frequencies in the range of 50 kilohertz, and this frequency, high frequency current, can be transmitted through the capacitive loop. And this transmission can be performed as a serial resonance circuit when you also add some inductances in this, and the resonance frequency of this can be adjusted with the AC-AC converter at earth potential. And this high frequency AC current can be then used to feed a rectifier at high voltage potential, and this rectifier then generates the high DC current inside the test loop. And that this is actually really working, you see here this at this picture. So we have injected a current of 3,200 amps at a potential of 660 kV. So this is really working, this concept, and you can inject a high DC current at a high DC voltage. So the next topic in our project is the testing of the overvoltage performance. Remember, we have the test loop of approximately 100 meters. So you now would say, okay, 100 meters, let's put a lightning impulse voltage on it. We want to make a superimposed test, which means DC and then a lightning impulse on that. And you would expect such a shape. And when you would do this, you would get not this, you would get this here. So this means you will get some oscillations on your lightning impulse. And why is this like that? Well, for 100 meters loop, you will get some traveling wave effects. The propagation time for 100 meters would be in the range of 300 nanoseconds. And so you get reflections due to traveling waves across your assembly. And this can result in higher voltages at positions on the Hvdc GIS. So this means that you make the test more critical as it should be. So maybe you provoke a flashover, but this is not because the system is not well designed, it's because the testing is not well designed. So this means that you have to make something to improve the testing. And well, the easiest approach is that you use higher front times for the testing, and there are two possible solutions to achieve this. You can make higher front times with a conventional lightning impulse, or you can make higher front times also with an oscillating impulse. Here, both oscillograms are shown. Some words for oscillating impulse voltages, they are used for on-site testing. So when you make an impulse testing at site, and the generators for this testing are quite compact. Both solutions are possible in general, but when you now look on the technical details for a generator with a lightning impulse and for oscillating impulse, you will see that the charging energy is 270 kilojoule for a lightning impulse generator for our technical ratings, while Oli would just need 30 kilojoule. The charging voltage is quite much more, 1.8 to 1.2 megavolt, and also the height and the weight of such a generator is much higher. So you see also OLI is a very efficient solution to test the overvoltage performance of this large GIL assembly. And especially the last points, you have transportable devices, you can make it more compact in the high voltage laboratory. These were also some arguments for using the OLI in this new designed HVDC test facility. So we also decided to use OLI for our testing of the overvoltage performance. Now, the last question is superimposed voltage tests. There are also generally two possible technical solutions to make such tests. So we want to perform 1140 kV OLI tests with 550 kV DC. There are two solutions. They were not presented yet, but perhaps you already know this. You can use a coupling capacitor or you can use a spark gap. A coupling capacitor adds the impulse voltage to the DC voltage. The spark gap directly connects the impulse voltage to the device under test. And there you also see the two differences. And here are three arguments which were for us the major arguments for our decision. And well, for a coupling capacitor, you will need a higher generator output because you have to overcome the DC voltage for bipolar testing. So you will need approximately 1700 kV generator output, while you still only need 1200 kV generator output for the spark gap. This is also an argument when you design a new HVDC lab. So again, spark gaps is a higher invest compared to a very low invest spark gap. And also one argument which is quite important when you make such a big test. The highest voltage when you use a coupling capacitor in your circuit is 1700 kV. The highest voltage in your overall circuit for a coupling capacitor, for a spark gap testing, is 1200 kV. So if something fails in your test assembly, your device under test will get here for a spark gap only 1200, and here it could be maximum 1700. So you see a spark gap is fail safe while a coupling capacitor is not fail safe. For us, these were main arguments to say, okay, we will go the way with the spark gap, and so also we decided to use the spark gap. And also spark gap is this actually really works, especially for oscillating impulse voltages. It works much better than for conventional testing. Here you see some oscillograms in our test facility for oscillating lightning impulse and switching impulse testing. You see you get a very smooth curve for the testing of bipolar and unipolar testing. And what else is interesting, that you also can achieve it, that you test 550 kV DC even with less than 2 times the DC voltage amplitude of a switching impulse voltage. This is also possible with this configuration. So, and this is it. This was all I would like to present to you. Hopefully this was interesting, and thank you very much for your kind attention, and feel free to ask questions.
Thank you, Martin, for the great presentation. We are also very good in the time, almost exactly as planned. This was the last presentation of the technology and dielectrics session of the first session. So now we have around 15 to 20 minutes for a discussion. And already during the presentations, now a lot of questions came in. Please feel free to add more questions in case you have, especially to the last one. I would like to kick off the question round with maybe a general question that's not so much focused on one specific presentation. It is by Yuri Soloveyev from Hitachi ABB Power Grids. It's a general question basically to the whole WorkPackage 15. It would be good to know more about previous experience in development and tests of HVDC GIS before this project. There are a number of realized HVDC GIS like BPA and an ABB project in the 1990s. And also a project in the USSR. And can you maybe highlight the differences of the tests that we have realized in promotion? So actually, I would like to hand this question to the promotion WorkPackage 15 task WorkPackage leader, Uwe. Maybe you can say a few words. You also much about the historical background of this.
Yes, of course. Yuri, thank you very much for the question. So yes, of course, and we have used all the experiences from the older projects, especially from the BPA project. What I have to say here is that for this, especially for this project, BPA project, and conventional ACGS was used with a higher rating, used for a lower rating for a DC. What we have now is a DC specific design, so a new generation, and that is valid for all manufacturers from Japan and from Europe. So we have a completely new design, especially for the insulators. And within the promotion project, we have focused on describing test methods and test procedures. So that is really new, that we have developed in the project and together with CKA and ISC, new test procedures focusing in the promotion project on this prototype installation test.
Thanks a lot, guys. Yeah, thanks.
Thank you for the answer, Uwe. And with this, I would like to then go to the first presentation, questions to the first presentation, HVDC GIS in Japan. First question by Maria Kosse from Siemens Energy. First of all, thank you for the presentation. And then Sato-san, why have you changed insulation material in the installation in Hokuto converter station in comparison to key channeling? It was on slide 11. Sato-san, can you maybe elaborate a bit on this?
Yes, so may I take control of this screen?
Yeah, you can feel free to share.
Just a moment. Can you see my presentation file?
Yes.
Yes, and which page?
Slide 11, please.
Slide 11. This one?
Yes. And this, the question is, why does this converter station here that you present here have as a different insulation material compared to the heat channeling?
Okay. So this was compliant to the latest material. I mean, same as HGIS. And of course, both for HGIS and HGIS, we attempted to reinforce the insulation function. So only we applied the latest material for the insulation. Is this clear for you?
Yes, thank you very much.
Okay. Thank you for answering this question. The next question is from Walter Hohlaus from Hvac in Switzerland. Did you also change the shape of the DC GIS spacer to improve for dielectrics?
Yes.
For you,
Yes, with many apologies for my poor explanation, but I couldn't explain all of the aspects of the GIS. But the point is how to realize compactness and also resilience of the GIS. And between the first Hvdc GIS and the second one, the shape, not only the shape of the insulating spacer, but also the size of whole total GIS was changed. So automatically we developed new insulating spacer to apply the second Hvdc GIS development.
Okay. Yeah, thank you very much for the answer. There's another question from Alain Giraudet, Supergrid Institute. Also, I'd like to express this, thanks for the good presentation. And the question is, could you please explain why DCGIS needs a special surge arrestor with lower LI protection level? Is it also the case or necessary for AIS DC substations?
My answer is it depends on the case, and but maybe your comment is on this specification. So at the time when we applied the first Hvdc GIS to key channel, we not only by manufacturer but also by the utility, we investigated all the case of the relation between rated voltage and also LIWV. So we found that at that time LIWV is 3 times of rated voltage. So but in consideration of the coordination all of the system, we found that we can coordinate with the surge arrest technology. We can reduce the LIWV, and also it would contribute to realize the compact Hvdc GIS for mainly for 500 kV. So maybe you can see in this table, or for 500 kV Hvdc GIS, rated voltage is 500 kV, but LIWV was 1300 kV. So it means around 2.6 times of the rated voltage. So we could realize the compactness of the first Hvdc GIS.
Okay, thank you. And another question from Uwe. Has a special test been defined as a type test in Japan to verify the effectiveness of the particle trap?
So at that time, it is somewhat difficult for us to identify which one is a type test and which one is routine test, because that was the first and only one project for Hvdc GIS project. So we agreed, we means not only the manufacturer but also the utility to verify how the traps would work well or not. So not only the factory but also the field verification test, we checked the particle final particle location after the DC application, and we found that the trap worked very well. But I think it is not defined as type test, only for verification. This is my understanding.
Okay. Yeah, thank you. Maybe connected to this, another question: how did you decide on the specifications? I mean, probably also no standards available. So did you decide for the main specifications for the key channel HVDC link and the new Hokkaido Honshu HVDC link, for example, as you show on the slide?
Okay, so for each project, we mainly carried out the simulation, mainly surge impulse simulation and also transient overvoltage simulation. And we checked the waveform and the maximum value of the surge, simulated surge. Then we defined the specification for each project.
Okay, thank you. And one final question. I can't really identify the name, but the question is, how exactly are the enclosure return currents taken into consideration for HVDC GIS duct?
Return current. For the field commercial products, we considered very well. But as you know, in the laboratory test, there is some limitation to realize the phenomena completely same as the field. So some cases we only ground it with the enclosure. Does it make sense to the question?
From my side, it's logical. In case for the original question doesn't fit just to the original asker, please put it into the chat. But from my side, I would continue. Sato-san, thank you very much for answering this question. I think it has raised great interest in the audience. So thank you all also for these questions on the HVDC GIS in Japan presentation. And with this,
thank you very much to you.
And with this, I would like to go to the questions to the next presentation by Nadu, testing of HVDC GIS. The first question by Uwe is also kind of an overall question. After performing the long-term prototype installation test, do you see the need to change the test procedure for standardization?
Yeah, I think that's a very good question. Well, I think there are lots of lessons that we've learned from doing these tests. Of course, it requires more discussion which tests should be taken into account, which tests should be added more, I guess. That requires discussion. The testing of prototype installation itself, I'm not sure if it is kind of mandatory in itself. I believe it is mentioned in some documents as an option. So yeah, I think maybe there is already discussion in IEC of this of DCGIS working group. Yeah, for me, yeah, we just have to take some lessons which we got from this testing actually.
Okay, thank you. The next question from Professor Klaus Neumann. Did you find particles at any location at the final inspection?
Well, yeah, that's an interesting question actually. We have done our best to find out any particular. Yeah, we have looked at the critical locations in the DCGIS, but there is nothing that we could see. In this case, it looks like I showed some photos on the presentation. Actually, it looked like brand new and as if it was never subjected to stress before. Yeah.
Yeah. Thanks. Then a question from Salia Abdul Madhar. Did you also monitor the average current during the PD monitoring? What does the PD activity of the GIS look like? Anything notable or very robust with no pulses?
I think I would like to reflect this question back to you because the PD online monitoring was performed by Hitachi ABB colleagues actually. Maybe you can say some words there. I guess Uwe or Michael.
I can say a few words from the PD monitoring with UHF that we had running as a kind of a commercial system. So we couldn't really identify any DC PD from inside the test object. What was a great challenge throughout the test was that from a EMC standpoint, it was quite a noisy environment. The test hall was in the middle of an industrial park. There was also some construction going on. There was, I think, a training facility for the fire department behind it. So we quite often saw a lot of noise on the system. And with DC, it is more challenging to identify it really as a noise because you don't have the the AC voltage as a reference signal to identify any noise. So I think this was the challenge. We also worked with an antenna, but also we have now analyzed the data with more detail after the test. We have not found any PD source inside, but it's definitely more challenging with the DC to filter out the noise in a real environment. That's maybe a conclusion we can say from manufacturer side after this long-term test.
Yeah. The background noise was really an issue as far as I remember also.
Yes. And then maybe a more encompassing question, what were the main challenges in performing such a long duration test?
Yeah, that's also a good question actually. Well, the long-term test itself explained actually it is challenging to keep everything up and running for more than 1 year. To get the lab space and time is also another thing. If you don't even consider the logistic to set up the complete GIS installation in a laboratory, plus the monitoring actually. So our test engineers must monitor the whole system 24/7. That means if there is any issue coming up, they must be immediately solve it. Otherwise, if the test is interrupted, there is another procedure which will even delay more. So those are the kinds of challenges. All the sources must be running continuously and also monitor the measurements. It's more of a practical challenge actually. Yeah.
Okay, thank you. With this, I would like to conclude the questions specifically to your presentation and go to the next one, which was my presentation on the, let's say, more manufacturer side of the prototype installation test. One question from Bhavesh Acharya from Hitachi ABB Power Grids. Actually, what is the difference in inside painting between AC and DC GIS? I can take it myself. So one decisive question that you can easily see is the different color. So we use more of a pinkish color for AC and this green color for DC, but the color is just let's say a function or an effect of the main function. I can say we have adapted the conductivity of the paint for DC. I would not go into more details on what we did exactly there. And the next question is from Thomas Götz, Technische Universität Dresden. And his question is, how does the optical PT measurement system works? Which measurement principle is used? So the system that we have had included in the long-term test used quite a sensitive photo multiplier to detect possible discharges. And we had connected it during the test through to several or to specific compartments where we saw the chance for maybe a higher chance to see some PD, but in fact during the test we did not see anything from them. And to more details of how it works, I would also not go too much into detail during this question round. And with this actually I also had one question before about the general PD measurement with UHF. I would actually conclude the questions about the prototype installation test for GIS and would go on to the GIL prototype installation test, the presentation by Martin Hallas. And here again, a question from Thomas from TU Dresden. Do you have, Martin, do you have any information about the firing, extinguishing of the used spark gap for the OLI, OSI? Do you always get the shown wave shapes independent from the spark gap configuration?
Yes, I hope you hear me.
Yes.
Okay.
Loud and clear.
Thank you very much for the question. So, you should see my screen. So it's like that for OSI, mainly it looks like that as shown on this slide. There are some different wave shapes for unipolar testing. For unipolar testing, when you have especially a very large gap distance and a very low voltage compared to the DC voltage, you may get the effect that the OLI voltage is not going to 0 kV, but it's going to the DC voltage level. Something like that can happen. And also when you have not far enough and too close, then during this process, you can also get some refiring of the spark gap when you have this process. Perhaps the second question goes in the direction if something extinguishes because of the oscillations. We have made many tests with oscillating impulse voltages, and we have never observed this effect. Even when you have zero crossings in your voltage shape, you do not have a spontaneous extinguishing during the voltage shape during the testing. So this I can share as an information.
Thank you. The next question is from Hong Hei from DNVGL. How do you manage to trigger the spark gap with Li voltage less than 2 times 550 kV? Is there a special trigger system?
Yes, this is also a good question. So actually, no. I triggered the question a little bit, I know, but no, there is no trigger mechanism in the spark gap. It's working naturally because of the OLI voltage. So there is a certain effect which comes with that. It's here on this slide. I've copied them fast here inside the presentation. So when you just have here, this is the electrical circuit. You have here the generator which generates here the oscillating switching voltage. You have here the generator generating the DC voltage and the device under test, which is mainly a capacitance here. So, and when you now have a spark gap and the spark gap here connects it directly, you get the overall shape like that. You have an oscillating impulse voltage and the capacitance is quite high, so you get such a shape. Now imagine one slide further, you do not have connected the device under test for the generator here. Then you just have the assembly here and then you have no capacitance. You have just a small earth stray capacitance, which will be fed with this impulse. And there you get a very high and very steep voltage, which is generated here on the one electrode of the spark gap. And this voltage overshoot naturally triggers the spark gap without any trigger mechanisms. This works for OLI quite well. When you would like to make such tests with conventional voltage shapes, then you need a trigger mechanism, yes.
Okay, thanks. And one final question from Takeru-san. Thank you, Martin, for the presentation. Can you give some more details of the DC high current feeding scheme with 70 kilohertz through the capacitor, especially on the rectifier, including its cooling method and 70 kilohertz generator at ground level?
Yes, I also copied here from another conference some slides together. Here you see the rectifier, and is a good question because it's not able to make at 50 kilohertz one transformer who transforms our high frequency and high voltage signal to a 3050 amps high frequency signal and then use one rectifier who rectifies then this at high frequency. This is not possible. So we are using a concept with several modules in parallel. So we get here our high frequency signal. It's around 2.5 kV and 60 amps in maximum. And then we use several transformers in serial connection of the primary winding, and the secondary winding is connected in parallel. So by that, each transformer only gets a small amount of the rating, and also on the secondary winding, also only a small amount of rating. But with connecting them together, you get the overall high rating you want, you like. And then each secondary winding of the transformer has an M2 rectifier, and this M2 rectifier is feeding a busbar, and this busbar then collects all the currents together. And the cooling device, here it's shown such a module. The cooling device, it's working with a passive cooling device. It's it's a normal passive diode. It has a voltage drop of approximately half a volt. And this cooling device also has some fan here to blow the heat out. But it nearly works also without this fan cooling. And the converter itself uses a similar approach. It's also, again, that you use several modules, connect them again in serial and parallel, and make a summation of all the signals together, and then to transmit the power. And then here also, there is no liquid cooling device. We have also here, it's enough to use cooling devices with fans, especially because here MOSFETs are used to generate the high frequencies and not IGBTs.
Okay, thanks. Yeah, I allow one final question. If you could please answer it maybe quite shortly. It's from Andreas Voss, Hevli. The question about oscillating Li and spark gap versus a regular Li that's maybe also created with the coupling capacitor. Can it be considered as identical for the stress of the equipment, or is there a difference? Because it looks quite different from the wave shape and from the integral.
Also a good question. So we have investigated this in also several pre-tests here in our laboratory on scaled arrangement, and we have not yet published anything from these investigations. Right now, I can share the information that up to now the data looks like that oscillating impulse voltage is nearly the same stress for the insulation, for the insulator, and also for the gas gap than for a conventional lightning impulse. More an oscillating impulse is even a more critical testing with the front times we are applying in our test facility than a conventional lightning impulse. But yes, as I have said, further publications will be available in future for that topic.
Okay. Thank you very much, Martin. And with this, we're slightly over time, but I would like to take the chance to say thanks for the good discussion, for the presentation. And I would like to hand over back to Uwe.
You are muted, Uwe. Uwe, you are muted.
Yeah. Oh, thank you, Michael. So thank you very much. We are a little bit over time, so I propose to restart in 15 minutes, so 11:25 CET. I use the time for a break, coffee break or so, then we will meet us again in 15 minutes, 11:25. Thank you. See you.
Okay, see you.
Yep. So hello, welcome back to the second session, and I will directly hand over to Nadu.
Yes.
The second session. Yep.
Yes. Thank you. Welcome back. I hope. Well, we have still 1 minute, of course. So, welcome back, everybody. Welcome to the second session of this workshop. In this session, we will be looking at applications and standardization activities. You will get 5 interesting presentations in this session. Two on actual applications from a TSO perspective, and 3 related with international working groups, 1 from IEC and 2 from SIGRE working group. The first presentation is on an update on IEC Technical Committee 17 by Mr. Motoharu Shiki from Toshiba Electric. Yes, yeah. Mr. Shiki is a convener of Working Group 6 of IEC Technical Committee 17, which is a common clause for DC switchgear. I guess he will give us his experience there. He's been working with Toshiba Energy System Solutions Corporation in the switchgear design development group in high voltage switchgear department. And with this, I will give the screen to Mr. Motoharu Shiki. Please present your slides. Mr.
Yes, yes. Just a moment. Can you see the slide?
Yes, I can see your screen. If you can make it big, yeah.
Thank you.
Good.
Okay. Thank you for introducing me. I'm Motoharu Shiki. I'm the convener of the ICTC70 working group 6. I'd like to talk about the status of the preparing the standards for DC switchgear. This is a relationship among technical committee and subcommittees in IC related to Hvdc. There are technical committees dealing with horizontal standards above the technical committees for each apparatus standard. TC99 deals with installation coordination and system engineering of high voltage electrical power installation. And TC115 deals with high voltage direct current transmission for DC voltage above 100 kV. Switchgear is dealt by TC17 and its subcommittees. Needless to say, international standards exist for AC switchgear, but for DC switchgear, there is no standards at the moment. Considering this situation, ICTC17 decided to organize working groups to prepare standards for DC switchgear. Six working groups are launched. And working group 6 deals with common specification, and working 63 deals with bypass switches and paralleling switches. And working 64 is for DCCB, and working 65 for current transfer switches, and working 66 is for disconnectors and earthing switches. And working 43 deals with GIS and GIL. They are now preparing standards simultaneously. And they started with technical specification before international standards. And the schedule for publication is 2022 and early 2023. From this slide, I'd like to talk about the status and the points of the draft for common specification. Here is the status, and our first draft was circulated on November last year, and to national committees, and comment acceptance is closed on the first day of this year. And now working group 6 is starting to prepare second draft, considering of the comments from the national committees. And here is the items including the different points from AC specification. First is the rated voltage and the insulation level. The second is the superimposed impulse voltage test. The third is the routine dielectric test. And fourth is the continuous current test. And the last is the short time withstand current test. Concerning rated voltage and insulation level, standard values are now under consideration in joint working group 13 between TC99 and TC115. Joint working group 13 deals with only HVDC but not MVDC. And so working group 6 decided that the rated voltage and the insulation level will be determined within working group 6, not waiting for the outcome from joint working group 13. The values are determined by referring to the existing project values, related cigarette technical brochures, IEEE standards, Chinese standards, and the draft of the joint working group 13. Next is superimposed impulse voltage test. Is introduced into the new technical specification. As you well know, this test have been recommended by SIGRE joint working group between D1 and B3. And in this test, impulse voltage are superimposed to the rated DC voltage. The impulse voltage are both the rated lightning impulse and the switching impulse voltage. Next is about the routine dielectric test. As a routine dielectric test, test with AC short duration power frequency voltage is specified as the first method. Of course, short duration DC voltage test can be applied. Okay. Concerning continuous current test, in the continuous current test, AC test current is allowed to use in place of the DC test current for convenience of the testing. Since AC resistance is higher than DC resistance due to skin effect, AC test current values should be reduced as the loss becomes the same as the case of the DC current. Finally, concerning short-time withstand current test, in this test, AC test current is also allowed to use instead of DC current for convenience of the test. But the correction of the skin effect is not allowed in this case. And the peak values should be kept as the same values as the case of the DC current for verification against the electromagnetic force. Here is the conclusion. 6 working groups were launched, and now they are preparing draft of the technical specification of DC switchgear. Target year for publication is 2022. Working Group 6 is preparing the technical specification of common specification for DC switchgear. And I briefly explained the difference point of the DC specification from the AC specification. And that's all from me. Thank you for your attention.
Thank you, Shiki-san, for your presentation and update on ongoing activities in IEC. We look forward to the final publications of the working group because they are really important also. I would like to ask the audience to write their questions in the chat box. I will collect them and later, of course, bring back for discussion. Then we will proceed to the next presentation. The next presentation is from Alex Alefrakis of TenneT, who is talking about design consideration for DC GIS applications for HVDC offshore bipole grid connected systems of TenneT. Just a brief introduction about Alex. Alex Alefrakis is HVDC technologist in the asset management department of TenneT TSO, is currently the technical lead of TenneT for HVDC developments in the 2 gigawatt program, which covers a project portfolio of at least 12 gigawatt until 2030. His fields of expertise focus on HVDC system and station design, multi-terminal systems. He holds MSc in Sustainable Energy Technologies from TU Delft and MSc in Electrical Power Engineering from Technical University of Athens. Alex, I give the control of the screen for your presentation.
Thank you, Nadia. Thank you. I will just try to see. Do you see my screen already, or?
It's black. I see the screen, but it's somehow covered. Now it's good.
All right. Yeah. So hello to everyone. Yes, I will give a short presentation about the new 2 gigawatt offshore HVDC standard of TenneT, and to briefly explain some system design aspects which are relevant to the application of DC GIS. The main point of my presentation will focus on a brief introduction of the TenneT portfolio in the offshore developments, the relevant design aspects. I will briefly explain them, and I will also spend a few words on the standardization strategy of TenneT regarding these connections. To begin with,
Alex, can you put on presentation mode of your screen? Maybe that's better.
It is on presentation mode.
Maybe you shared the PowerPoint and not the screen. Then we see, because you see not the presentation mode.
I will try again. So it should be the PowerPoint file, correct?
Yes. Still the same, maybe.
This is the presentation file.
Maybe if you put it on read mode, perhaps it works. The next one, the next button to the presentation mode.
No, I don't have another option.
Then you can also proceed with that. That's also fine.
Yeah, I hope it is still visible. If something is not, please let me know. I would like to begin with setting the scene with regards to the 2 gigawatt applications. We have a roadmap for TenneT with several grid connection systems to go in operation before 2030 in both the Netherlands and Germany. The majority of the almost all the connection systems have to be ready for operation between 2028 and 2030. So the tender procedures will start very soon. It is important to note that some of the connections, the ones in the Netherlands, will also have a multi-terminal readiness commitment. And there is also, this is the short-term, let's say, plan. And of course, this is a growing portfolio. And after 2030, the mid-term plan also has to do also with the so-called North Sea Wind Power Hub, which is a consortium between TenneT, Gasunie, and Energinet, where the creation of energy hubs in the North Sea is discussed. And there, when it comes to the electrical infrastructure, again, 2 gigawatt 525 kV building blocks are the base case. So as you see, TenneT is preparing, let's say, a new standard, which we expect to be, let's say, the new base case for the HVDC infrastructure from now on. And there is a very obvious continuity of projects also after 2030. A few words about the standard itself. It's, as I said, based on 525 kV nominal voltage. It's a bipole application with a metallic return cable, 6 kV on the AC side, on the platform side, with a fixed transformer arrangement. We're aiming for a standardized platform design. And important again to say that the system will be multi-terminal ready on the offshore side, which means that the platform itself has the extra space which is needed for the future components.
Alex, we see still slide 3. We have to go.
I don't know what I will try to share then the screen.
I guess I have the presentation. Maybe shall I put it for you, perhaps?
Yeah, if it's perhaps it's better.
Okay, just a second there. So,
yeah, I was in slide 4 then.
Yes.
Yeah. So this is just a brief outlook of the single line diagram. with the main features. And I was just saying that the single line diagram also has some additional features with regards to the multi-terminal readiness. And it is also our intention to standardize to a certain extent also the arrangement of the AC and the DC switch yards. So we can go to the next slide.
Yes.
Okay. Okay, that's strange. Nevertheless, what we mean by multi-terminal readiness, yeah, its definition is that the system should not prevent the future extension to a multi-terminal system. You see below the picture, for some reason it's not illustrated correctly, but nevertheless, it shows the possibility to connect our point-to-point HVDC systems to another offshore terminal and then to the grid of UK. In that sense, it will be a 4-terminal system, and the second topology where our offshore platform will be connecting directly to the UK side for a 3-terminal application. In both scenarios, this would mean that the DC yard of the platform station would have to have one additional departure line towards the UK. Next slide.
Yeah.
Yes. While referring to the single line diagram, we have an area which we call AC yard converter side. This is the switch yard area between the converter transformers and the converter valves on the platform. This here we have in this slide a generic single line diagram of the high voltage components that we expect to have in that particular area. What is important to note is the mixed voltage profile due to the bipole application and also due to the way that the voltage is modulated. You see the arrangement of the components that we are interested in. Those components will be, this will be a standardized arrangement for those components. The only option in this arrangement will be the presence of a circuit breaker. At the moment, because we rely at the moment on air-insulated equipment, there are no circuit breakers because this will be this would require a lot of additional space reservations. So it is at the moment introduced as an option in our considerations. So the braking capability is not, let's say, part of the base case, but it is an option because it has certain, of course, operational advantages. If we go to the next slide, it's just a brief list. It's just a few items that we have extracted from a longer list of design parameters. It's an envelope of parameters which are relevant to the design of switchgear. And this is an envelope that we have created based, of course, on our own internal studies, and also based on figures that we expect such a product to have in general. And we can go to the next slide.
Yeah.
This is the generic single line diagram representation of the DC yards on the DC side of the converter valves now. This is the 525 kV. Where here it's quite obvious how the extendability of the DC yards would look like for the multi-terminal application. So the base case is that we should be referring to the upper figure, where we have again a standardized arrangement of the high voltage components. And the lower figure is the one that illustrates the extension of the switchyard for the multi-terminal application. So space reservations on our platforms will be there for the future multi-terminal extension. And again here you see that we have some optional objects in the single line diagram, which is something that we are still trying to explore as part of a market consultation we are currently performing together with DNVGL. to understand from the market the capabilities of equipment with regards to current making and breaking tasks, let's say. And this is also illustrated in the next slide, which is a list again of data. This is again, let's say, a shortened version of the list of parameters we have addressed to the market to explore whether a HbDcgs product is feasible. And the last area of application in the 2 gigawatt standard is the so-called neutral yard. In the next slide. In the Bible scheme, we have a neutral yard. On the upper figure, you see the part of the arrangement of the neutral yard for the point-to-point connection. And the lower figure again shows you the extension modifications that are needed for the multi-terminal operation of the system. Again, with some optional components as part of the scheme. The exact determination of the components is also dependent on suppliers' capabilities. And in any case, they are driven by the functional requirements that Tenet is specifying for on a system level. And the next slide, I believe, is the last one from my side. Some main key messages from this short presentation is that there is an overall ambition for Tenet to strive for SF6-free HVDC platforms with a global warming potential of less than 1 for the alternative gases. At the same time, we are aiming for a standardized platform design because of the very big portfolio of projects. We consider it as a very essential, let's say, objective to have. And of course, it is associated with significant de-risking of the project. And at the same time, the standardized features of the platform should also allow for extendability of the electrical areas for the multi-terminal applications. In that respect, we do not focus only on the short-term applications, but also to the mid-term applications where we will try to convert the 2 gigawatt platforms, standardized platforms, into hub stations. So the application of HbDcgs will become even more essential to end up with cost-effective solutions. So this was in brief the presentation from my side. I apologize for not being able to present it properly. So I hope it was clear enough. If not, we can of course discuss further during the wrap-up session afterwards.
No, it's okay. It's fine, Alex. Thank you very much for your presentation. Now we'll proceed with the next presentation. So the next presentation is also an application of a HbDcgs, possible application of a HbDcgs by TSO, that is by Mr. Frank Richter from 50 Hertz Transmission. Just to introduce Frank, he has a degree in electrical engineering. He has started his career in developments of medium voltage equipment and vacuum circuit breakers in a French company. In 2008, he joined the manufacturer in development of high voltage circuit breakers in Germany. Since 2014, he worked as an asset manager for high voltage equipment in a German TSO. He is a member of SIGRE Study Committee S3, and since 2014, he is secretary of the study committee. He's an author of different publications, mainly within SIGRE. With this, I would like to invite Frank to proceed with this presentation.
So hello, also from my side. I hope you could see my presentation now. It's okay?
Yes.
Nadia?
Yes.
Okay, so I would like to start my presentation. I would like to show some possible applications and requirements in our grid for DC grid. I have concentrated a little bit more to onshore applications as the previous speaker has already looked at offshore, so maybe I would like to add something. And maybe at first we are also aiming to install our first application of a DC grid onshore, because we would like to gain experience with this equipment. And onshore, the accessibility is more feasible, and the integration, the grid is also more flexible onshore as offshore. Okay, Nadia already introduced myself. So I structured my presentation as follows. So at first, I would like to start with a background, why the use of a DCGS is essential or why it's needed. And then I will present some examples of the application and the advantages of a DCGS. Afterwards, I try to show some technical parameters for the design. For the moment, it's not really easy to say that or to rely on it, because the values are strongly depend on the converter technology and the system requirements which you have. And for the moment, we are not sure how we will operate our system, and also to how our system will look like. And at the end, I will give a short summary. So let's start. So the background of everything is our energy transition. You see the phase out in Germany of the nuclear power production in 2022. And by that, also to increase the share of the renewable energies for electricity. So for the Germans, 2030 should be 65% of renewables should be integrated. Now it was increased in the past. It was before 55%. And by 2050, it should be 80%. The ambitions of 50 Hertz are a little bit extended. So we would like to achieve 100% of the renewables at 2032 already. Because you see, in 2019, we already implemented 50% of our power consumption by 50%. So these requirements that these requirements of the integration to the grid leads to a need of extension or expansion of the grid, which is presented here. Maybe for overall Germany, it's shown here. It's in DC line 2,400 kilometers, or interconnectors, which means to other TSOs 330 kilometers. And I put it only for 50 Hertz here, which is the east part of Germany. Means DC line 340 kilometers, or interconnector 70 kilometers. So here you see the first thoughts to implement a DC switchgear. So maybe we have for these lines, we have we think about to have cable section substations, which means you have a cable on the right side, on the left side, and you have the cable in different substations. So that means you could test these cable sections, not the substations, or the cable section itself could be tested with AC voltage. So because the length is not so long and the power for testing which is needed is not so high. That's the first approach. The next thing is, if you have fault on the cable, you have a better or more accurate cable fault location, which you could have. Maybe if you could imagine that you have 1% failure there, and if the cable is the cable length is too high, then maybe you have to look at 6 kilometers length where the fault is. And if you have smaller sections, then maybe the fault location could be located more accurate. At the next things, we have the transition from the sea to the land cable. Then maybe we have also such a substation. And another possibility is we have a procurement of different cables from different suppliers. So we have we could have different lots on the market. And you see here, maybe also for some reasons, it's allowed not to have only cables for DC, also DC lines are allowed. And then we have a transition substation, which comes from a cable to a line. Or here is shown, maybe sometimes the authorities not allow us to build such an open space substation or insulated substation. It must be a building around, but you know, when you have the transition from the sea to the land cable, then maybe it's near to the beach, and yeah, who likes such an open substation there, so that we have the requirement to build a building around. So here maybe it's a comparison done for the open space or for the air insulated substations and compared with the gas insulated ones. So that means that you have a lot of space savings there, which you already know, I guess, because it's shown in some a lot of publications. So it means 90% for cables substation and 80% for a cable overhead line substation. The next thing, maybe it's more interesting. If you have an AIS substation which you need the building to the authorities, you see it on the right side. Here is a AIS DC substation in a building. Here is the secondary part, or maybe the control system, protection system, and so on. And these are the AIS DC primary equipment is here. See the height of the building. And on the right side, you see the same thing if you use it as a Hvdc Gis. And you see the size is not determining by the primary equipment. It's more or less the secondary part of the control system and protection system, which determines the size of the substation, which is mentioned here. So some values which you see here. So the area which is needed is 43 meters by 34 meters. Could you reduce to 27 meters by 28 meters? Maybe it's more determined by the secondary systems. And the height, maybe it was 20 meters before, and now it's only 8 meters, which results in the building costs, which only, I consider only the building costs, which are now 100% here on the AIS side. Could you reduce by up to 30% at the DC side, which makes a lot of savings. I would like to give also some values. Maybe my colleague before showed you some values. It's quite difficult to give a really good values on that, because the system studies are still ongoing. And if you could consider, if you have a line and you have both systems on this line, maybe DC and AC, then you could have failures between the systems, and that you have to consider. Even also, as you explain, if you have an open switchgear, and you have maybe a cable switchgear also in the building, then maybe lightning impulse is not so important to consider, so that you could you reduce the lightning impulse values. Maybe we have already some existing installations which 420 kVAR. Maybe then for new installations we plan it with 350 or 550 kV. The rated current will be up to 4000 amps. Rated short circuit less than 40 kA, and maybe for the peak 56 kA. Lightning impulse, as you already see it in your previous presentations. We plan all our installations. We plan indoor, and so the ambient temperature should be between -5 degrees and +40 degrees. And what is also very important is, if you use a GIS, a DC GIS, then the interfaces must be tested, and as I see you here, there's the first cable test from one manufacturer. I have it here, Sweet Cable or Sumitomo. It's a link here, which already test a cable with the DC GIS together. So maybe that's very important that you not have only the DC GIS for us as a user, that you also have the interfaces tested. So it's not necessary to discuss with the different suppliers for the different for the different equipment. When it comes together, who's responsible for the interface? So and the next point is, you see the DC GIS is a quite new product on the market, but SF6 is on a big discussion for the environment, and we would like to prefer solutions with a low GBP insulation media. Not SF6. So maybe we would prefer to have some other things, maybe air, or what you have already seen on the market for the AC GIS. Finally, I summarize. So what are the drivers and the benefits? So the drivers, I think also that the DC GIS is a model for the mesh DC grid. And a DC grid will be the infrastructure of the future, which we would like to deliver. And HbDcgs is a very efficient and compact technology which we could use. And maybe also the driver is that the tested interfaces are now available so that we could use it. And the benefits for us as user are space-saving installations. So maybe, as I already mentioned, the onshore is up to approximately 90% less and the offshore up to 80% less. So it means lower investment and lower operating costs. So maybe if the building is not so big, then also the operation costs are not so high. The next thing is aesthetic substation design. So maybe we have an increased acceptance by the community. Maybe as I explained, so near to the beach, a building is it's accepted more than in EAS substation. It's a big part of discussion, and also the approval authorities maybe have an easier life with us if we have it in a building. And as I explained, we could also optimize the overall system. Maybe if we do not need such high lightning impulse voltage levels, or maybe we can also reduce everything. So the converter design could be a little bit smaller and so on. So thank you very much. That was my presentation. And if you have questions, maybe we could discuss about afterwards. Thank you very much.
Thank you, Frank, for your interesting presentation. Well, of course, questions will be there. Please feel free to write down in the chat box. We will ask Frank later. We will now proceed with the next presentation. The next presentation is about secret joint working group D1B357 on the dielectric testing of gas-insulated HVDC system. This is presented by Professor Klaus Neumann. Just to introduce Professor Neumann a little bit, he studied electrical engineering at Technical University of Aachen with main focus on power engineering. Subsequently engaged as a test engineer in a high voltage laboratory of a switchgear manufacturer. From 1979 till 2010 with RWE at different positions involved in the field of high voltage equipment and systems. Finally, with the German TSO, Amprion, responsible for operative asset management. Professor Neumann is a member of VDE and SIGRE, momentary convener of joint working group, for which he is going to present, of course, this session. A lot of publications. I would like to invite Professor Neumann to proceed with his presentation.
Yes, could you see my presentation?
Yes.
Okay.
That's it.
Okay, then let's start. Thank you very much for having the opportunity to share with you some information about the work of the SIGRE working group, D1B3.57, dielectric testing of gas-insulated systems. Yes, let's come back to the background. As we heard in the introduction this morning, the development of the DC transmission technology is progressing quickly, and therefore gas-insulated DC systems are of special interest. Hvdc Gis, due to their space-saving features, we heard of that, and DCGIL in particular in case of environmental concerns about overhead lines. At the moment, no standard for dielectric testing of gas-insulated HVDC systems are in place, and therefore it was decided in the past to create a SIGRE working group. And this SIGRE working group studied and discussed the fundamental phenomena of DC gas-insulated systems under DC and under transient voltage stress. And after studying and after finalizing this discussion, the dielectric testing procedure was established, which some parts of them I will present soon. The complete work of the working group will be published in a technical brochure, I think, rather soon. What are the basic phenomena? which mostly affect the insulation performance of gas-insulated HVDC systems. First, we have to mention surface charge accumulation at the insulators that will reduce the breakdown voltage at DC voltage, but in particular at superimposed lighting or switching voltage. And the other phenomena are the metallic particles. We have to take into account when the lift of field strength is exceeded, the particle starts to move on to the high voltage conductor that causes this firefly phenomena, or the particles are bouncing between the conductor and the enclosure, and that strongly reduce the breakdown voltage. Let's consider these basic phenomena and the insulation properties at DC voltage stress. First, we have to take into account that when we energize a gas-insulated system directly after DC voltage application, there is a capacity field distribution relevant depending on the capacitances and on the material permittivity, as it is like at AC voltage. With time, there is a field transition into a resistive field distribution, and that is mainly determined by the material conductivity and also by further influencing factors. And this field transition is accompanied by charge accumulation at the insulator surface and in the bulk of the insulators. And further, the duration of the field transition to the steady state DC condition that is mainly influenced by the insulator geometry and the material. Yes, let's study the phenomena at the DC voltage stress at gas-insulated interfaces and the field transition. For the charging process, three principal mechanisms can be given: the volume conductivity in the solid material, the surface conductivity along this solid surface, and the gas conductivity due to the ion drift in the gas. And the duration of the capacitive to the resistive field transition strongly influenced by the material conductivity, but it is also the surface and the volume conductivity is also a function of the electric field, of the temperature, and of the humidity. And I will give you an example of this temperature dependence. Here you can see here the transition time T90, that is the transition to the 90% of the DC steady state status. And you can see here there is a strong dependence on the temperature, but there is not only a dependence on the temperature, but also on the temperature distribution. That also influences the insulation characteristic of the gas-insulated devices strongly here. As you can see here, there is the development of the DC field depending at different locations of the insulator here, depending on the ambient temperature. And you can see here the ambient temperature at 40 degrees Celsius. It's much faster than at 20 degrees Celsius. The temperature distribution influences the insulation characteristic. Also, you can see here there is a temperature gradient of 0. That means it is a more or less cold condition. And then here along the insulator there is a distribution which is relevant under high load condition. you can see here there is a strong movement of the high electric field region to the enclosure. So furthermore, the influence of the accumulated surface charge by the DC stress has to be taken into account. Here on the left-hand side, you can see the case of switching impulse voltage, and you can we can regard here, we can observe a strong reduction of the breakdown voltage depending on the surface charge accumulated. On the left-hand side, on the right-hand side, the same is to be seen for the lightning impulse voltage. In particular, as you can see here, with opposite polarity, there is a strong decrease of the breakdown voltage. A strong decrease means about, in this case here, about 30%. I have to mention that it is related to the pre-stress of only 30 minutes. I'm very sure if the DC pre-stress is longer there, the reduction will stronger. The other phenomenon is the particles and the particle motion. When a gas insulated system is contaminated by metallic particles, as I said before, the particles can move between the HV conductor and the enclosure, and under DC voltage, the particle motion is potentially more harmful than under AC voltage. And we can observe two types of particle motion. As you can see here, after the lift off field strength is exceeded, the particles starts to move. Either we can observe the standing motion or a bouncing motion, depending on the polarity. The two main characteristics can be observed at negative polarity, the so-called firefly phenomenon, and at positive polarity, the bouncing motion. And we have to apply mitigation measures for improving the insulation performance against metallic particles, that is insulating coating, and installation of particle traps. You have seen this particle trap, which is mainly applied in Japan, but other particles are also applied here, a trap integrated in the conductor, or a trap with multiple notches integrated at the enclosure side. Yes, what can we learn when we want to prove the capability to withstand these phenomena I've mentioned in the gas insulated system? First, we want to consider the insulator in the gas insulated environment. If we energize the gas insulated system, we have to consider this interface charging of the solid gas surface and the space charge accumulation in the solid insulation until the resistive steady state is reached. And this transition to the DC feed distribution depends on the local temperature distribution and on the lowest temperature. And this transition could lead to a long test duration of hours or months. That means the design of the solid insulating components, as well as the right testing procedure, is of importance for the verification of the electrical insulation behavior. Let's have a look to the temporal evolution of the electrical field of the solid gas interface. Here you can see the evolution. On the left-hand side, it is the maximum electric field is normalized. The light blue is the relative the temperature change, and you can see here that the maximum electric field stress occurs at the beginning of the DC stress period or at the end under the DC state conditions and the maximum temperature gradient conditions. That is true for typical sigma, yeah, but that's also true for high sigma, which can be used as another material parameter. That means it is independent on the insulator geometry that can be derived from this figure here and from the material properties. And that has consequences for dielectric testing, in particular, if we take into account these so-called composite voltages. Here, what are the consequences for these composite voltages? That means the superposition of the impulse voltage to the DC voltage, which should simulate the overvoltage stress during service. That means after relative short DC pre-stress of about 2 hours and cold conditions, there is without any temperature gradient across the insulator, that could be a critical case, but also after long DC pre-stress to reach the DC steady state. And the worst case temperature conditions with the maximum temperature gradient across the insulators. And that means additional testing during the transition time is not necessary. And with this knowledge, an insulation system test was developed and suggested to demonstrate a satisfactory electrical performance of the insulation system consisting of insulators in the gas-insulated environment. And I want to make you familiar with the test procedure that is given here in this table after a pre-test, which contains also this superimposed voltage test with a short pre-stress. Long duration continuous DC voltage test is applied. The duration of these tests can be calculated or can be evaluated by simulations or by real charge testing on surface charge testing. After these superimposed lightning and switching voltage tests are applied, both bipolar and unipolar superposition, and then the polarity is changed. The polarity reversal or the test is done with the other polarity in the same way as mentioned before, and finalized by superimposed lightning and switching voltage tests. The basic test circuit is given here in this figure here. You can see here yellow marked, that is the gas insulated system that is fed by this DC voltage source, and also for heating the DC current source is here given. And for superposition of the impulse voltage, a DC impulse generator should be available. Here that gives a figure of the setup for such an insulation system. Here you can see here that is the device under test. It contains here 5 pieces of each support insulators or of partition type insulators. And on the left-hand side, you can see here the different devices, testing devices here. That is the test object. And here you can see here the DC voltage and here that is the impulse voltage, and it is coupled here by a spark gap. Now, what is with regard to the particle and the particle motion? There is PD testing is of interest. As we have learned, free moving particles can reduce the breakdown voltage, and different countermeasures have to be applied. But there is no phase correlation of the PD pulses as it is given at AC, and therefore we have to use other methods. We have to use the so-called statistical pulse sequence analysis for defect identification. This sketch here shows the different impulses. Here, the first impulse and then subsequent impulses. And for statistical analysis, we use the correlation of the amplitude of the different pulses, or of the time differences of the different pulses here, or of the differences in amplitude related to the time differences. And in this case here, I have shown 6 correlations, and yes, these 6 correlations can be used for defect identification. Here, this figure shows some defect patterns recorded in the lab. This row shows a conductor particle adhering at the particle, that is the so-called firefly mode. And this here is a protrusion on the high voltage conductor. As you can see here, different patterns can be acquired. And I want to compare that with patterns which are acquired during this prototype installation test. You can see here there is a certain equivalence between the first row here gained in the lab and these rows here recorded at the prototype installation test on site. And the decision is that probably particle adhering at the inner conductor are not yet captured by the trap. Okay, probably short brief information which further topics were discussed by the joint working group. First, these more information and more suggestions are given with regard to the prototype installation test. Long intensive discussion in the working group were with regard to with regard to the necessity of this test here, but as a matter of fact, there's a little service experience or little information about the long-term performance of the gas-insulated DC technology available, and therefore this test is reasonable, and the objectives are to collect more service experience by long-term tests before installing this pilot, before installing a pilot installation in the grid. That should be the next step then, and to demonstrate the readiness of the level of this type of HVDC equipment. I think that is what was also the basis for the promotion project. The test sequence here is given here. It is similar to that you have seen before. 3 sequences, 2 high load sequences and 1 zero load sequence. And in this case, these high load sequences are subdivided in different subsequences here, and after each subsequence, either lightning impulse, superimposed voltage, or switching impulse, superimposed voltage is applied. And finally, a condition check will be carried out. further, the test considerations were done with regard to the test equipment and the test procedure, and this presentation is based on the testing experience gained up to now, and it should give guidance to the user. Here you can see here a suggestion for the superimposed impulse voltage here. You know, different options are available of coupling and blocking this superimposed voltage here generated by the impulse generator. It can be coupled by spark gap and by capacitor. And in this chapter, the different advantages and disadvantages are presented to give guidance to the user which he has to expect if he will use which circuit. Then the test equipment, and this chapter also deals with the prototype installation test. It shows the options of current injection of high potential. Mr. Martin Hallas just showed a very sophisticated procedure. And
Professor, if you could summarize, we're running over time.
That is the last. This is superposition of the oscillation of the OLI and OSI and the test interruption and pauses. And finally, chapter deals with the testing of the interface between DC cables and DC gas insulated systems, and I'm sure that will be dealt with more in detail in the next presentation. Let's conclude. Two basic phenomena mostly affect the insulation performance of the gas-insulated systems: surface charge accumulation and particles. And adequate testing is recommended by the SIGRE working group, and that can prove the capability of gas-insulated HVDC systems being able to withstand these phenomena, and can demonstrate the technical readiness level of the technology. And me, the convener of this working group, has appreciated very much the fruitful cooperation of the working group members. Thank you for your attention.
Thank you, Professor Newman, for a very insightful presentation. I guess a lot can be discussed had it been not for time. We are a little bit over time. I would suggest again the audience to raise their questions through the chat box. Then we proceed with the last, but definitely not the least, presentation of this session. This is a presentation on another joint SIGRE working group between B1, B3, D1 79, which is recommendations for dielectric testing of HVDC gas insulated system cable sealing in, which will be presented by Kes, Cornelis Plate actually. Well, Kes is the technical coordinator of a promotion project. You have seen him this morning. I guess many of you know him. He has done excellent work for promotion. I don't need to introduce further. Kes, please proceed with your presentation.
Yeah, thank you very much, Nadu. So it was already mentioned by a few people today that HVDC GIS also needs to be connected to something, and that something is typically a cable. We already saw a few different possibilities here. For example, the use in offshore substations, where well, most likely these will be connected by cables, submarine cables, but we also saw a few applications on land. And this brings a bit of a problem, because if we don't have a proper cable interface, then we end up with something like this, where we have to use a connection through air, with an air termination on the cable and an air termination on the GIS. And this would kind of defeat the whole purpose of having a GIS, because this, of course, takes a lot of space. Now, the good news is that several designs for HVDC GIS cable connection assemblies exist, and they can follow similar sort of high-level arrangements as you see in AC. So we have, for example, dry type terminations or so-called fluid-filled terminations, which for DC are mostly not filled with fluid but with a gas, SF6. And then there are also some designs where the type has not been disclosed, so who knows what's inside. There is a problem though with these designs, and that is that we don't really know yet exactly how to test these. So we can have two different types of tests. There are the cable tests, as have been described in the C-grade technical brochure 496 for HVDC cables with extruded insulation. And then on the other side, there are the tests which were just presented by Professor Neumann from the C-grade Joint Working Group D1B357. And they are not the same. And the question is, how should we then test this cable connection assembly? Which test should we apply, and which one is the tougher of the tests? And if we have tested it according to one test procedure, should we then retest it using another one, for example? To be a little bit more specific about the differences, in a very crude comparison, you could say that the HVDC cable test philosophy is to test the cable's ability to withstand the operational stresses that are applied to it during service time, and also the aging that takes place over the cable's lifetime. When you look at the HVDC GIS related tests, they are more focused on testing the GIS ability to withstand the operational stresses, but not so much aging phenomena, as this doesn't take place as much as in cables. And this means that there are different load cycle sequences and durations. The DC test voltages in the cable tests are generally higher than in the HVDC tests. The impulse test voltages for the GIS are higher than those for the cable, and the test currents used in the HVDC GIS are also higher than those used in the cable. So the question that we are trying to address in our working group is not to come up with new test requirements, but to actually find out which of those two different test procedures is more tough than the other one, and does it really cover all the stresses. And the idea here is to basically check if the cable tests, the PQ test and the type tests, if they are in principle sufficient to cover all of the stresses that are being exerted during an HVDC GIS test. Because if that is the case, then we can simply test the cable connection assembly as part of the HVDC cable PQ and type test, and we do not have to repeat any additional tests for this type of component. So that is the goal of this joint working group, to develop these dielectric testing guidelines for HVDC GIS cable connection assemblies by comparing the simulated internal stresses caused by the HVDC GIS testing requirements and the HVDC cable testing requirements to determine which is the most severe case. And if this isn't the case, if, for example, there's a situation where the HVDC GIS test requirements are tougher than those for the cable tests, we will have to probably start a new task similar to what Professor Neumann just presented in actually defining new testing requirements additional to existing test procedures. Well, the general approach that we have is to model the GIS cable connection assemblies and then simulate the stresses from the cable test requirements and the GIS test requirements in a specific test object arrangement. Then use predefined criteria to compare these different stress profiles and use that to formulate a recommendation. The idea is to do this for the designs for cable connection assemblies from different manufacturers. Different manufacturers are taking part, fortunately, in our working group. And then also do this for the different types of tests, so qualification tests, manufacturing tests, and decommissioning tests. We carried out a survey to find out what is already on the market, and a first feedback on the survey is, for example, about the voltage ratings, that there's quite clearly two different voltage classes, so to speak, one around 320 kV and the other one around 525 kV. So we will consider both voltage classes. Then another one, and this question also came up earlier in the presentations, is about the dimensions that are used in the design of the cable connection assemblies. So for AC, there are standard dimensions defined in the IEC 62271-209, and we asked the manufacturers if they follow the same dimensions, and some of them said yes, but interestingly, some also said no, and they have their own bespoke dimensions for their cable connection assembly design. Should be noted that when it says fluid filled, for example, in the IEC 62271, this really refers to a set of dimensions, for example, long or short dimensions, which can then also be used in the HVDC version, except that it doesn't mean that it has to be fluid filled. So it could actually be a dry type design with the dimensions of a fluid filled type cable connection assembly. Then we looked at the different types of cable termination arrangements or designs that are out there, and the significant share was made up by the fluid filled design. So in this case, it would be SF6 filled, but dry type designs also exist. And then lastly, we wanted to know a little bit about whether the material properties are comparable, and in most cases that seems to be the case. So like every good piece of work should start, we started with limiting our scope to bring a little bit of focus into our working group. So we will consider the existing standards, the C-grade TB 496 and 622, and then the test requirements from the working group D1 B357. We will focus first on the cable connection assemblies that use the standardized dimensions from the IEC standard. We will consider voltage classes of 320 and 525 kV. We will only focus on cables with extruded insulation, kind of assuming that cables with mass impregnated insulation will not be used to be connected to an HVDC GIS. And we will focus for now on designs with SF6 insulation. To start, our focus will be on the qualification tests, so PQ tests and type tests, or we could also call these long-term tests in a way. So the idea is to compare what happens in PQ tests with the prototype installation test, for example. And we will also consider the after installation tests and the impact of those. Right now, we started about just over a year ago, and we are at the phase where we are developing the guideline for modeling and simulation. So I just wanted to give a brief example of that. We have several vendors in our working group, and as you can imagine, they do not want to share the details of their designs with the other vendors in the working group. So we've decided that each vendor will carry out their own simulations. But of course, we want to know that the conclusions or the results from these simulations are comparable in terms of the quality and the depth of the simulation. So we have set out the task with a guideline for how should the different vendors model their cable connection assembly designs and how should they simulate them, so that the results of these different simulations are all based on the same common assumptions, same common simplifications, and the same common boundary conditions. What you can see here is, for example, how do we deal with the presence of the flange on the left? Can we simplify that by removing it and simply stating a few boundary conditions in terms of potential and temperature there, to simplify the simulations and speed up the calculation work as well, of course. So a little bit about the progress that we have. We finished creating an overview of the different types of applications of HVDC GIS. We created a technology overview to see what type of technology is out there and how can that steer the development of the testing requirements. We carried out a comparative analysis of the different testing standards for cables and GIS. we worked on an overview of different types of test setups and to also develop a guideline about how to make choices for what type of test setup or test circuit to choose. We finished the development of a guideline for modeling and simulation of these HVDC GIS cable connection assemblies. We are now working on a definition for the simulation scenarios and also a guideline for how to compare the outcomes of the simulations. And we are carrying out a simulation trial run to see if the guideline for modeling and simulating these assemblies is indeed complete enough. And then, of course, the next step after all of this is being completed is to actually simulate the actual vendor-specific HVDC GIS cable connection assemblies and compare and evaluate the results of it, and hopefully move straight to formulating the requirements and the recommendations for testing. It could, of course, be that we have another task if it is clear that, for example, the cable-related tests are not covering all the GIS test-related stresses. We may have to continue and go a little bit more in detail to formulate additional testing requirements. That was my presentation. Thank you for your attention, and I'm open for any questions.
Thank you very much, Gis, for your nice presentation. Well, that was all from the presenters. I would like to thank all of the 5 presenters for their very nice contributions. Now the floor is open for questions and answers. We have some questions from the audience, of course. I will try to put them in maybe perhaps in accordance of appearance. Well, the first question is to Shiki-san from Hrodet Align. From Supergrid Institute. Of course, he thanks Shiki-san. He's asking, please, do you intend to introduce in the standard the possibility to perform oscillating wave in replacement of lightning impulse test to be in line with the test performed at TU Darmstadt? Shiki-san, if you can comment a little bit about that.
Okay, thank you. Thank you for important comment. I'd like to discuss this issue within working group 6.
Oh.
Okay. So point is oscillating impulse is severe than lightning impulse or switching impulse.
Okay, if you stop sharing your screen. Case? Yeah, sorry, continue, Shiki-san.
Yeah. You don't hear me?
No, I do.
Yeah, okay. I think this comment is very important. So I'd like to discuss this point, this issue within working group 6.
Okay. There is another question, of course, from Frank Richter, who also presented in this session. Are there already rated values fixed in the standard, like insulation levels, for example, in
yes.
your group?
Yes, other ratings were determined in our draft, such as duration of the short circuit or peak withstand current.
Okay, good. Maybe if you could also comment on why you're not considering a skin effect when you apply a short time withstand test.
Yeah.
Can you say a few words about that?
Yes. The skin effect for the short time, very short time duration is very complex, and also it is considered to influence of the skin effect is considered to be small in the very short time.
Okay, thank you. Then I will proceed to questions for Alex. There is a question from Kes from DNVGL again. Thank you. If you could comment, Alex, if you could comment on the choice of earthing the neutral position offshore and not onshore? How is the neutral earthing point realized offshore? Will there be another current transformer measuring any possible earth current? That is what he would like to know, because he did not see that in your single line diagram. Alex, can you say a few words about it?
Yeah, those questions, I think they're more related to the system design. There has been a preference from TenneT to have the solid grounding arrangement on the offshore side. That was the original preference for a number of system design reasons, also controllability reasons. From the more in-depth analysis that was performed last year, also by suppliers, we saw that this preference is not essential anymore, in the sense that from insulation coordination point of view, and also from a single line diagram point of view, the advantages that we originally expected are not that dominating anymore. And the grounding in the bipole is not only for voltage referencing purposes, for also different purposes. Therefore, this remained as a preference, is not a requirement of ours. So what you saw in the first generic single line today was just an illustration and not more than that. For the designs that the grounding will be on the offshore side, what you saw in the neutral yard single line from the presentation today, it was only covering parts of the neutral yard, not the complete arrangement of the neutral yard. So this is why it was perhaps a bit misleading. And of course, there would be a CT for protection purposes, and there is no other CT except for transformer protection, of course, on the offshore environment. So yes, there would be a CT as part of the arrangement in the grounding. But they would never lead to CE electrodes, for example, or this kind of solutions, if that was the intention of the question.
Okay. Maybe if you say a few words about any concrete plans of TenneT on the use of WDC GIS, could be.
Yeah, thanks for this question. For the 525 kV offshore, I can only comment on the 525 kV offshore installations. As I said in my presentation, we will start the tenders for those systems rather soon. And based on the readiness level of the technology in combination with our ambition to strive for alternative gases, we have chosen to not specify for DC GIS application. For the DC yards, this will be left open to the manufacturers to propose as part of their EPC, let's say, tenders. For the area between the transformers and the converters, we have decided for standardization purposes to ask for air-insulated equipment. So for the short-term projects, one of the areas will be based on air-insulated, and the DC yard will be open for suppliers to propose, also while taking into account the multi-terminal extendability options that we have in place.
Thank you. It was a very good answer. There was a question from Uwe from Hitachi ABB, also both for Alex and Frank. How do you feel about the question of continuous monitoring? Will you generally demand that, and if so, which monitoring methods should be used? If you could comment, maybe first Alex, and then I will continue with Frank, because there are also other questions to Frank.
Perhaps I can give the floor to my colleague Max Tucek to answer this question. He's more relevant. Yeah.
Yes, thank you.
This
is Max Tucek. I'm the technical expert for GIS and therefore involved in the 2 gigawatt program. We will, of course, require density monitoring for the GIS systems, and furthermore, we are interested in partial discharge monitoring, knowing that this is, of course, not a proven system so far, and that we have to learn on this system. But we are interested in. Thank you.
Good, thank you. The next question is, of course, the same question applies to Frank. Frank, can you say a few words about it?
Yes, sure. So maybe for the gas monitoring system, of course, yeah, we will require it. And even with the SF6, the insulation level, we need a monitoring system there because the requirements for reporting and so on will increase in the future, and so we require at least these as a monitoring system. About the other systems, I don't think about it yet, so maybe I have to leave this question a little bit open. But to say, maybe the monitoring system is not only to prevent faults. So in my opinion, I would say a monitoring system has to be also able to give information, to have some overstress on the equipment maybe for the future. That could be another application for monitoring systems, that you could say, depending on the condition of the equipment, you could have more voltage or more current on it. So that maybe could be a solution in the moment for monitoring systems.
Okay, thank you. A question from Kes for you to Frank again.
Yeah.
He would like to know about the reduction in cost of buildings as a result of using GIS.
Yeah.
Can you say something about it?
For the moment, I don't know exactly because I don't know the price of a Hvdc Gis for the moment. So maybe we are evaluating that. But you see there's some space. I see that could be a little bit more expensive, but I don't know it by heart.
Okay, yeah. The next question is from Michael, who also presented this morning to Frank from Hitachi. So it's an interesting presentation. Oh.
Nadio, I could not.
Just one moment, please. Sorry.
Yeah.
I can read the question myself, if I may, Nadu. So the question was, the figures you presented on slide 5, very impressive about the renewable transmission. And the question was just, it's 50%, are they related to a power or to a peak value, or are 50% of the total energy transferred over the year from renewable sources?
Yeah, I could answer that. It's
sorry for that. I had some disturbance at the background. Okay,
no problem.
Please proceed. Yeah.
No, it's not the average over the years, the 50%. It's more the peak which is installed in the grid compared to the total consumption of power which is in our grid. So maybe we have a definite amount, and the installed power which is by the new renewable energy resources, it's 50% of that now. But it's not the average over the year. It's more a peak.
Okay. Thanks.
So also the 100%, which is mentioned in 2032, it's not mean by that 100% could be delivered over the whole year by the renewables. There will be days which you always need nuclear or the coal-fired power plants to deliver the power.
Okay, good. There is also a question related to slide number 10 of yours from Martin Hallas of TU Darmstadt. Do you demand such tests for any available cable and GIS combination? How do you feel about separation of cable testing and GIS testing by implementation of standard for the accessory and GIS shape like for AC? There is a standard mentioned there, 62271-209.
Yeah,
if you could say something about it.
Yeah, sure. And maybe the presentation of Gis, he shows it quite impressive or quite visible. You see, if you test a cable or you test a GIS in combination, then you will have an overload of something, because it's not only in one direction. If you have one test, it's more overstress for the GIS, and the other test is more overstress for the cable. And I would say I would agree if there's you need the combination, and I would agree if you have a common standard which a test is like the -209, then maybe I agree on it. It's not necessary to have every cable or every GIS combination tested. So if the common standard is agreed, then I am fine with that. But in the moment, it's like this: that you test the cable and you test the GIS, then you have an overstress on one part of the both things, and that could not be here, like he said explained.
Yeah, thank you very much, Frank. The next question is to Professor Newman. So it's a question from Luis Castro Heredia from TU Delft about the insulating coating of the compartment and the metallic traps. are there metallic particles of are metallic particles a matter of concern and worth researching? In addition, how likely is that those particles actually occur? Professor, if you could say a few words about it.
Yes. Theoretically, it's not a problem if everything is well designed, if the coating is efficient and or the particle traps are efficient. But from the practical point of view, it is quite obvious that the efficiency could be not the best, and therefore not all particles are captured. And as you have, as we have seen from the results of our Japanese colleagues, some particles are not really trapped and captured, and they could be active any longer. From my personal experience, I can say that it is rather difficult to capture all the particles, and therefore it is interesting to identify those particles. And therefore, I'm very happy to find option to identify these by the PSA method.